Check, check, 1, 2, 1, 2.
Anyone's out there?
Anyone there? If we speak, you're the audio is good? Oh, you're trying right now. Okay. I just tell me,
Yeah. What is the correct pronunciation?
I5, yes.
All right. Just want to make sure, because I heard a few.
Yeah, I see.
Variants, I don't know. I want to get
see,
it right the way you like.
No, it's unpronounceable.
Yeah.
It was supposed to be a pronounceable acronym, but the NSF forced us to
make it, yeah.
well, it had to be I. And once you have the
All right, folks, we're gonna get started. All right, so welcome to the afternoon session. My name is Sergey Glazer, and we have a number of great talks this afternoon. And the very first one is by Jesse Taylor from MIT and the NSF AI Institute for AI and Fundamental Interactions, IFI, on interpretable machine learning for particle physics.
Great. Thanks, Sergey. Thanks to the organizers for having me. It's really wonderful to be here in PHYSTAT for the PHYSTAT community here in Imperial College London. Before I start my talk on interpretable machine learning, let me just take this moment to advertise this AI Institute, the NSF Institute for Artificial Intelligence and Fundamental Interactions, that's bringing together the deep learning and deep thinking communities to try to get a deeper understanding of our universe, as well as on how intelligence works. And for those of you who are at or anticipating the postdoctoral career stage, I want to let you know about our IFI postdoctoral fellowship program. We've been having this for a number of years. In fact, one of our IFI fellows, Gaia Grosso, is going to be speaking later today. And application deadline is for October 9th. And if you're interested in fusing together insights from physics and from artificial intelligence, please come join us in the Boston area. And then also, we have a series of summer schools and workshops, most recently at MIT in this past August, where also we do training and education of the next generation of AI and physics enthusiasts. And so, of course, the statistics community, the machine learning community, they have some overlap. So if you're interested in any of these things, consider IFI in your future. So today I've been asked to talk about interpretability, and this is going to be one of the workshop themes of PHYSTAT. And just to remind you that at PHYSTAT here, we're trying to emphasize some of the statistical issues involved. And one of the questions that I've asked myself is, what does it really mean for machine learning to be interpretable? And I am not going to answer that question exactly in this talk. You'll see what I'll do in a moment. So what does it mean to be interpretable? And there's other words that fall into the orbit of interpretability: explainability, trustworthy, safe, robust, aligned, helpful, transparent. You can ask, what do these terms mean? And in particular, what do they mean from a statistical perspective? And there's going to be talks on Thursday morning exploring this in some more detail. There's also going to be a poster session this Tuesday, today. And if you are giving a talk on interpretability for posterity, I'd like to put them on this slide to just give a sense for future people who look at these slide decks, what people are thinking about interpretability in 2024. For this particular talk, of course, the obligatory apology that the examples are drawn heavily from my own research, and that research is in collider physics, but I will try to bring in some other perspectives as well. Now, I'm speaking on Tuesday. The other sessions are on Thursday. And unfortunately, for various annoying reasons, but good reasons, I'm not able to be here on Thursday. So we have this very weird split situation where I'm giving kind of an introductory overview, and then the actual meat and content is going to be 2 days later, and I'm not going to be there for it. So I apologize for that. There are important things at MIT that I'm sorry I just have to go to, though in my heart, PHYSTAT is more important. And this is being recorded, so my apologies to the people who know where I'm supposed to be on Thursday. So what I need to do is I need to give you a very clear impression of my perspective, such that you can think about these issues on Thursday. And if nothing else, I want you to take the following away. And you can disagree with what I'm going to say now, but I at least want to give you a perspective so you can fight back on it. What does it really mean for machine learning to be interpretable? In my perspective, that's evolving, is that the desire for human interpretability often arises when we imperfectly specify the task that we want to accomplish. And sometimes we sweep under the rug, using the word interpretability, some type of discomfort with our problem. And maybe we should think a little bit more clearly about what we're trying to accomplish when we use that word interpretability. And that as a community, and I count myself in this, we should really strive towards actionable goals for interpretability, telling ourselves, why are we even using that word? What do we hope to accomplish with it? And I'm going to give you two examples. One is thinking about interpretability as a strategy to qualitatively assess sources of systematic uncertainties. And I'm purposely using that word qualitative because I want someone in the audience to yell and say, no, it's quantitative. Well, I think it's qualitative, at least what I've seen thus far. Or another actionable goal is to identify low-rank structures in high-dimensional data sets. And there may be other reasons why we want to pursue interpretability. But again, the focus that I want you to carry in your brain is when we say the word interpretability, ask the question, why? Why do we want it to be interpretable? What's our goal for doing that? Now, this perspective actually was inspired a little bit by reading the discussion prompts from Indigo. So for each of the sessions here at PHYSTAT, there's a prompt to get you thinking. So if you haven't read them, they're fun. So let me just read this one. I don't know, who wrote this? You wrote this? Anonymous writers wrote this. There's the probably apocryphal story of a machine learning classifier learning to distinguish cats from dogs because in the training sample, all the cats were photographed curling up on living room couches while the dogs were running outdoors in fields. How do we ensure that the distinction between, say, signal and background is based on significant features in the data rather than on the particular way that soft particles are simulated? And can interpretability help us diagnose this? And in my mind, reading this, thinking about what does it mean for features to be significant in the data? What are we trying to guard against? And this is why I'm saying that one thing we're trying to guard against are various systematic issues. And so the extent to which interpretability can help us qualitatively assess sources of systematic uncertainty, that's saying, can we assess whether, for example, soft particle reconstruction is driving our decisions in a way that we may think is inappropriate? Okay, so this is one of the discussion prompts. Another prompt, just as we would not expect a 10-year-old to understand how a single hidden layer neural network works, why should a very sophisticated machine learning procedure be interpretable by a mere human physicist? Is it important for our methods to be interpretable, or is it just enough to check out their properties? Is interpretability becoming an unrealistic goal? And then my own parenthetical, and what is the point of fundamental physics anyway? Why are we in this room? What are we trying to accomplish? And to the extent that there's an actionable goal in this, that one of the things that we strive for in physics is to find descriptions that are as simple as possible, but no simpler for physical phenomena. And so in that sense, there's an actionable goal of trying to identify low-rank structures in high-dimensional data sets. And I'll give you some examples of this in this talk. So with that preamble, I'm going to kind of unpack what I just said a little bit more, confronting the black box, give you some case studies from my own research in jet classification, and then I'm going to completely run out of time, but I have some interesting things to say about foundation models that we can get to afterwards, or maybe I'm going to keep talking very fast and maybe I'll actually get to it. Okay, so this first part of the talk, to benefit from machine learning advances, we must ensure that our algorithmic choices align with our scientific goals. That's the point that I want to make here. So let's start off with just some statistics 101 and something that we've already talked about a couple of times today about neural likelihood ratio estimation and the likelihood ratio trick, which is a key example of simulation-based inference. So just somewhere on the page, same page. Let's say our goal in life is to estimate the likelihood ratio between two probability distributions, P and Q. What we have are training data, finite samples, capital P and capital Q. And we have some learnable function, f of x parameterized, let's say, by neural networks. And our goal is to learn the ratio of P over Q. If we introduce a loss functional, this is one that I like, maximum likelihood classifier loss, has this funny log and log f and f minus 1 terms. And if we optimize this, at least asymptotically, then the solution is that the argument min of the loss is indeed P over Q, and that's the likelihood ratio. And the value of the loss for this particular loss is the KL divergence. So this is all very standard stuff. And this is something that we might want to do. And if we want to look at it in its asymptotic form, I like to remind people that this is basically just doing Lagrangian mechanics. You take some action, you write down a Lagrangian for that action, you do the Euler-Lagrange equations, and the solution for that is you're learning F is P over Q. And Ben mentioned this earlier this morning, that this is an opportunity for us to shift our focus from solving problems to specifying them. If we can specify them in loss function form, we can do various types of optimization, let's say gradient descent optimization, and we find solutions to our problems. In this case, we have a solution that asymptotically is exactly what we want, of course, with real finite training samples and finite expressibility of F. You might not get exactly the likelihood ratio, but this is our way of estimating this particular quantity. So thus far, I've said nothing about interpretability, but a question that comes up when you do machine learning is someone will ask, well, what is the machine learning? It's like, what do you mean, what is machine learning? Well, for this loss function, the machine is learning an estimate of the likelihood ratio derived from sample data and regularized by the network architecture and training paradigm. And those words usually make people very unhappy because they say, no, but what did the machine really learn? It's like, it learned an estimate of the likelihood ratio. What more do you want? No, but I want to understand. Like the word machine learning attached to artificial intelligence, and somehow it's supposed to have some human meaning to it. And if you say, but I want to understand it, you could ask the question, do you really expect for your particular domain problem that the likelihood ratio is going to take on some particularly nice functional form that you could learn, for example, with symbolic regression? And for anyone who's done a quantum field theory calculation to sufficiently high loops, you have to remember that those calculations involve special functions that actually have no elementary representation. And so, okay, is it any more interpretable to write down some hypergeometric functions than just see the output of some neural network? And so, I mean, you can see I'm challenging this idea of interpretability in the sense that for the task that we do when we're doing optimization, if the goal is to learn something that humans can understand, that's a different goal than saying, I want to learn, for example, a likelihood ratio estimate. So it's not like we're completely stupid. I mean, there might be reasons why we do want it to be interpretable or explainable, trustworthy, safe, and so on. And first of all, there's completely valid scientific reasons. One is that we could be working in a non-asymptotic regime. And we don't know whether the Euler-Lagrange version of what I showed when you go to the finite samples, actually that matches up well. The training data might be biased in some way. The result could depend on poorly modeled features like this example of cats and dogs running in fields or sitting on couches. Limited ability to perform independent validation, need for compact symbolic expressions if you want to communicate it to someone or you want to code it up in an efficient way, or a desire to generalize away from a specific context and use information in one place and deploy it elsewhere. So those are completely valid scientific reasons where interpretability comes up. There's also sociological reasons that you may, hopefully you are not, but maybe the people you're trying to communicate are skeptical of algorithmic or statistical or computational reasoning. Hopefully that's not a problem for anyone here in this room. Maybe you need to explain your decisions to external stakeholders. Maybe you have a desire to manage risks from unforeseen outcomes. Now, these are all valid reasons, but they do suggest an imperfect specification of your initial goals. That if your goal is interpretability, well, that's maybe not really what you're trying to accomplish. Maybe you're actually worried about one of these other issues. And if you're worried about one of those other issues, then maybe you should design your network architecture and training paradigm in order to address those directly. So, for example, in my own research with the likelihood ratio trick, I've used likelihood ratios-based strategies for things that we will talk about at this meeting, detector unfolding, Monte Carlo reweighting, estimating resolutions. And in those cases, I really do not care whether the machine learning output is interpretable. What I want it to be is accurate. I want it to actually be as close as possible with quantified uncertainties to the actual asymptotic ratio of two probability distributions. And there are limitations, certainly in the work that I've done, in ways of assessing accuracy and quantifying uncertainties. But I don't think that interpretability is going to help me. That is, I don't want the computer to tell me what's going on. I just want the computer to do the right thing and give me error bars that I can trust with appropriate coverage. So for applications like this, the goal is, again, accuracy more than interpretability, and interpretability might even get in the way of it finding the in quotes, correct solution. And this issue about what interpretability means, it's not just in physics context. At MIT, there's a Schwarzman College of Computing, which is trying to galvanize computing innovation. And they have a branch called the Social and Ethical Responsibilities of Computing. And that branch is doing various case studies where they're looking at computing issues, formerly led by my colleague, Dave Kaiser. And he told me about this wonderful case study that they did about formal specifications and whether that's human interpretable or not. So this is a case study in a completely different field. This is a case study in planning and robotics using something that's called signal temporal logic. And in that field of signal temporal logic, I'm told that there's this whole formal specification of what it means to write down a plan. That plan is well specified and will actually accomplish the thing that you want to do. Okay. So in this particular case study, they studied the problem of capture the flag. So you're the blue dot and you want to capture the flag and you do not want to run into the red dot. And now you need to come up with a plan for how can you get the flag without having your opponents catch you. And what they did is they had the machine generate various outputs. Then they asked humans, is the result that you got valid? And are you confident in it? Okay. And so again, this particular formal specification here, this is the gold standard of interpretability in this area. It is said that if your machine can output in this form that satisfies these formal requirements, then it's interpretable. You can ask, well, can the human really interpret it? And the first thing that you realize is that humans are relatively incompetent. So this goes from 0 to 30. 30 means they got it right all the time. 0 means they got it right none of the time. And then 1 to 5 is how familiar they are with formal methods. And you see this curve is relatively horizontal, which means that even if you have expertise, you're still not very good at this problem, maybe a little bit of a gain. So we're relatively incompetent at being able to test whether machine output is actually valid or not. But experts, that is those who are saying that they're very familiar with formal specifications, whether or not they're right or wrong, they're very confident in their answer. And in fact, their confidence does not change whether their answer was correct or incorrect. I think what this says is that formal validity is a distinct goal from human verifiability. And we just need to be very careful when we talk about interpretability, that interpretability, at least colloquially, means humans understand. But that's a different thing than saying whether something is actually validly specified. And actually, computers are much better at checking whether something is actually correctly specified in this particular context. So in high energy physics, we talk about interpretability, and we're going to have posters and talks about it. And you can ask, in that context, what do we mean? This wonderful living review of machine learning and high energy physics, they have a really interesting categorization of interpretability under the category of uncertainty quantification. So that's the categorization that this living review uses. And I'd be curious, actually, whether the authors of these papers who are listed in this category would agree that the goal of their method is a type of uncertainty quantification. And then the question that I raised earlier is that, do these methods provide, is it really quantitative information or is it qualitative assessments of uncertainties? And at least what I've seen thus far, it gives me very interesting qualitative information about sources of systematics, but not necessarily quantifiable or actionable information. So this is maybe my call to you, in the context of fundamental physics, what is the actionable goal that we want to achieve when we say the word interpretability? And then secondarily, relevant for PHYSTAT is that are those goals actually statistically sound? So let me just give you some examples then in high energy physics about some goals that might be actionable. So one is thinking about interpretability really as a strategy for uncertainty quantification. And so this is an example of Shapley additive explanations. I'm not going to go into the details on this. It might be mentioned actually on Thursday, where the explicitly stated goal is to identify features in your data set that are driving decisions about classification. So you say, I'm trying to make some classification. In this case, it's particle physics, collider physics, trying to say, is this particular event coming from some signal channel or a background channel? If it is signal, which signal? If it's background, which background? And then you have, in this case, 12 features in the data that you might want to exploit for figuring out whether you have signal or background. And then you can use the SHAP strategy to identify which features were actually driving decision-making. Okay, so that's the explicit goal, to identify the features driving decisions about classification. But why? Like, why do I care what's driving the decisions on classification? What am I going to use that for? And in this case of the dogs and the cats and the grass and the couches, I think implicitly in that case, what we're trying to verify that the features that the machine is picking up on, or the features that are driving decision-making, are actually physically relevant. And so in that context, I would say that the actionable goal from having done this is to qualitatively assess the potential sources of systematic uncertainties. Here, qualitative, because all you're trying to identify are the things that are contributing most, are those ones that I trust. But trust, again, has this kind of non-numeric value to it. And so something we could think about is how we could actually try to put numbers to a method like this to try to decide to what extent we want to assign systematics that are large or small when the sorting of feature importance might be different than what we expected. But this is one thing that we might mean when we talk about interpretability. Another thing that we might mean by interpretability is knowledge distillation. And these are two examples from my colleagues at MIT in two different ways of trying to model nuclear binding energies. So you take a nucleus, you zap it with energy, and all the protons and neutrons fly apart from each other. And you want to know how much energy do you need to inject to do that. So nuclear binding energies are interesting functions of the number of protons, the number of neutrons, and other quantities. And here are two attempts at taking basically nuclear physics data tables for binding energies as well as for other quantities. One based on symbolic regression, where you're trying to find the simplest symbolic expression to try to model what this nuclear binding energy is. And then you can compare the ones that this particular regression strategy did, how it compared to the physics-derived Weizsäcker formula from 1935, which you can also ask, is this interpretable or not? It's certainly compact. These ones up here are even more compact. But this is a case of trying to distill a lot of information down into a lower dimensional representation of the information. There's another technique that came out of IPHY, and my colleague Mike Williams, who's IPHY deputy director, and his collaborators, where what they're trying to do is they're trying to take nuclear physics information and bottleneck it within a machine learning architecture such that the latent space has some interesting structure to it. And they enforce a linear structure on that latent space, and then they see what emerges for the types of learned representations. And what they find, interestingly, is that they can actually recover the nuclear shell model in this way. That is, in the fourth principal component of the latent space of the machine learning architecture, it has exactly these lines, these horizontal lines corresponding to fillings of nuclear shells, which is actually quite interesting. And what they say is that actually compared to this 1935 problem, they actually get some sense better results in the sense of more accurate, but with no loss of interpretability what's going on, in the sense that you could really point to physics things, particularly a nuclear shell model for this example for what's going on. But again, this is an example of an actionable goal of trying to identify low rank structures inside of high dimensional data sets, and the extent to which you can distill a lot of information down to a few salient features. That's the extent to which you'd say you can interpret what's going on. But these are examples of things: systematic uncertainties, low-rank structures. These are potential goals that we might have from interpretability. I'll be curious as to your thoughts about what other things we might do to replace interpretability with a more actionable definition. So what I want to do next is do some examples from my own work where I have used the word interpretability either correctly or incorrectly. But there is a lesson, and the lesson that I would draw from my own work is that when possible, if you are going to have interpretability as a goal, then try to pursue active interpretability, where you control the network architecture and training paradigm, which is distinct from a more passive type of interpretability, where you take an existing training neural network and then try to figure out what went on after the fact, to the extent that you can do something active, at least in my own experience, that has been more fruitful. I was looking back at various slide decks that I've put together over the years, and the more things change, the more they stay the same. So this is from slides that I was giving in 2019, where apparently I still talked about the likelihood ratio tricks and still talked about interpretability in machine learning. This came from a talk where we were introducing neural network architecture called energy flow networks that encoded the quantum field theory principle of infrared and collinear safety. And what we argued is that, oh, this is a powerful network, that it also was interpretable. And what did we mean by interpretability in 2019? We were very, very proud that we were able to look inside of the neural network and make visualizations of the neural network innards. And this is what it looked like. And you can ask, does this really count as interpretable? It probably counts as modern art. But this is trying to visualize a 256-dimensional latent space of a neural network. You can ask what you've learned from this. I mean, as someone who works a lot in quantum chromodynamics, like actually this is an amazing representation of the singularity structure, the collinear singularity structure of gauge theories. But I'm not sure that anyone else would recognize it in there. We did gain some genuine insights when we really made the latent dimension super small, down to L equals 2. But we said this is interpretable because you can plot it. And well, it's psychedelic. What does it mean? So what have I learned in the intervening years? So 3 lessons since 5 years ago, and highlighting the power of active interpretability. So one is that if you have a catalog of trusted observables, it is possible to translate black box machine learning algorithms on low-level inputs into simple classifiers on those high-level trusted features. So I'll just tell you what that technique is. Another lesson is that if there's simple operations like multiplications and sums, which I think we would agree don't really require interpretation, then you can just bake those into your machine learning architectures if you want. And then if there's some property that you want your network to have, make sure that you impose algorithmic guardrails. Otherwise, the machine might pursue undesirable optimization. So in my own brain, I put these 3 examples under the heading of interpretability. Though I should just mention that according to the Living Review of Hydrogen Physics and Machine Learning, these papers are categorized respectively as feature ranking, point cloud networks, and equivariance, that we can't even agree when we say the words. We're trying to get interpretability, whether we all agree what that is. But hopefully these examples are ones that are interesting to you. So the first one is about translating black box neural networks. And in this case, previously, before I was interested in machine learning, developed a basis for collider physics called energy flow polynomials. And energy flow polynomials are just polynomials of energies and angles. Hard to distill things to something that's at least more interpretable in the sense of like your eye can look at it and say, okay, you see something. Though again, you can ask whether likelihood ratios or any other thing that you might want to learn are well approximated by them. But you can ask whether you can select energy flow polynomials that mimic the decisions made by some computer vision algorithm. And so what this approach does is it iteratively builds an estimated likelihood ratio from this catalog of high-level observables by basically comparing some black box network to this catalog of observables and picking them off in a greedy algorithm fashion, one at a time, to kind of match the decision ordering that your black box algorithm is doing. And in this field that I work in jets and jet substructure, you can imagine alternative history. So this is the order in which things are selected. Each of these little pictures here represent a polynomial, where the node represents an angle, an energy, and an edge represents an angle. And it's interesting, as you go through, by the time you get to iteration 3, you find the most ubiquitous thing that's used in jet substructure, just counting the number of particles. When you get to iteration 6, you discover an observable that I introduced back in 2013. But this technique turns out to be more efficient than computationally efficient than kind of brute force ways of searching through this catalog. My complaint about this method is that this method is only as good as the trusted observables that you have. And there's a cryptic footnote inside this paper where it basically says, by the way, this basis may not be the best one. Maybe you want to consider this other basis. But I was vetoed by my collaborators. We just had to get the paper out and didn't actually have a chance of exploring what I felt was a more physically motivated basis. But again, if you have that motivated basis, you can then translate a black box algorithm into that motivated form. This is more recent work with two students, a graduate student at MIT, Rekhav Gambhir, and then a Bowdoin College undergraduate, Athis Asathapan. We call this moments of clarity, where what you're trying to do is you're trying to figure out within the context of a neural network whether you can build in certain types of operations that are either physically motivated or at least just mathematically motivated, that don't require that much interpretation. You can just say, oh yes, that's a reasonable operation to do. And one thing that you need to do is you need to decide what your pooling operation is. Very standard thing is to do max pooling or sum pooling. But also you can do moment pooling, where you take a collection of objects and compute various moments of that information. So what I said before with that psychedelic image, that corresponds to sum pooling, otherwise known as using the deep sets strategy, where you're taking per particle features, let's say weighted in some way, but you're basically just summing them. But once you do sums, that gives you kind of averages. You can imagine taking second moments or third moments or fourth moments. In this particular example here, this is doing a second moment pooling that you get covariances from. So it has the same philosophy and computational scaling as these energy flow networks. It just uses a new permutation invariant pooling operation. And then what this allows you to do is to use fewer per particle features to achieve the same performance. So actually, all you needed to do a particular discrimination task of telling the difference between quark jets and gluon jets, all you needed was one per particle feature. You just had to take up to 4 moments of it. And that mimics the classification performance of having 4 separate learned features. And then you can do grad student descent. So you can actually try to interpret what's going on by actually trying to write down various symbolic expressions motivated a little bit in part by the structure of QCD. And actually you can learn that this one single learned feature has this interesting logarithmic structure to it. So this is a type of symbolic regression, RG standing for Rekhav Gambhir, where he kind of searched through polynomial structures and ended up stumbling upon this log. Again, you can ask what you've learned from this, but at least it gives you more compact expressions that then you can scrutinize. So the last example is we're calling safe but incalculable. With that psychedelic image, I promised you that thing was representing the quantum field theory principle of infrared and collinear safety. And indeed, formally, it is safe. Now, the other words we say on top of that is that if you are infrared and collinear safe, then you can be computed order by order in perturbation theory, and that hadronization corrections are well under control. And that last part is not correct. That is not correct at all. And we learn this by trying to train an energy flow network to distinguish between parton level versus hadron level, which if you're really supposed to be insensitive, you shouldn't be able to tell the difference. And it was able to get a whopping huge AUC. And it's like, whoa, that's a problem. And the answer was that it was formally safe, but it was formally safe in a way where the machine had found, the loophole. And one way of talking about it in the language of regularization is that because we forgot to put a Lipschitz constraint on it, you ended up having something that vanished in a particular limit, but have a slope that basically was infinite. And so this work with Sam Brightoni, Ben Nachman. Brightoni is joining IPhi as an IPhi fellow this year. With this Lipschitz constraint, you can then actually have the desired features, and then as desired, parton versus hadron sensitivity drops to where it should be. That is, you should be insensitive. But in all these examples, you can ask whether or not these techniques count as interpretable. But their goal, or the reason why we design them in this way, is that we were trying to make them more robust to systematic effects. So that's, again, this actionable goal of addressing systematic uncertainties. Though I think, again, a complaint about this is that, well, what do we mean quantitatively? In this last example, okay, I can put this Lipschitz constraint in there, but how can I actually translate that into a number that says I've controlled systematic uncertainties to a particular degree? And so it's not clear actually how to quantify the level of improvement without some type of additional dedicated study. So my time is up as anticipated, so I'm not going to talk about foundation models. You can ask me about what I want to say about foundation models. But maybe the only thing I'll say is I'm unsure about the statistics of it, so we can talk about that in Q&A. But let me kind of just wrap up and just launching the discussion here, just reminding you. So just to say, like, I think it's human to have the human desire for human interpretability. But it seems to be, at least in my own case, that it's often I want that when I haven't really thought through, I haven't specified the task that we want to accomplish. We should strive towards actionable goals. Systematic uncertainties, our low rank structures are two examples of that. Curious to your thoughts about other kind of target goals for interpretability. But I have an immediate actionable goal right now, which is to start a vibrant discussion of interpretability here at PHYSTAT, and hopefully that can begin right now. Thanks so much.
Thank you very much, Jesse. I'm sure there are many questions.
Hi, thanks so much for the talk. I had a quick question about your term active interpretability. I can understand how some of these constraints that you build into the model help with, say, statistical efficiency by incorporating outside information to help with the model building. But in the context of interpretability as something that humans want, what is your sense for what active interpretability gives us?
So let's say you have a definition of what interpretability means. Then maybe you should write a neural network architecture that literally spits that out. So when I was still a machine learning skeptic, I was visiting a colleague in Italy, and he was telling me about, I forget if it was a student of his or a colleague of his, that was having a startup company. And essentially what that startup company was doing was rediscovering boosted decision trees. But the thing that they were providing for their client were sentences that said, the decision is being made for this reason. This quantity is big, therefore, you should make this investment. Now, our boosted decision trees aren't particularly powerful, but they are pretty easy to describe to someone. And so that's an example of something where you change the architecture, and that choice of architecture might have an immediate human form. Let me give you another example of this. So in the US, I don't know if it's true internationally, there's a credit score that says whether you can get a credit card or get a home loan. And where does that number come from? Okay, so it's some combination of information, but there are people at MIT who are trying to say, okay, when we spit out a number, the only thing that we're allowed to do with spitting out a number is that final number, let's say a credit score, has to be a sum over monotonic functions of well-defined features, such that if your income goes up, your credit score has to go up. If you have too many loans up, then your credit score has to go down, and you have no interactions or any nonlinearity. Well, it can be nonlinear within single features, but no interface between things. That's very easy to explain to someone. And if someone says, why was my bank loan rejected? It's not some wacko formula that you would say, oh, the reason why it was rejected is because you had this score, and this score comes from monotonic formulas relating quantities. So that's another meaning of active interpretability. You build the decision-making with a structure that aligns with what you'll ultimately deliver to a client or consumer. So that's one version of active interpretability.
We're going to go to Zoom next, and then we'll come back. Igor, would you like to speak your question?
Yes. Hi, Jesse.
Hi there.
So my question is the following. The thing is, the idea of regularization in classical statistics is pretty old, and we have maybe half a century experience with it, and we know what it engenders. It engenders bias and loss of information. So, and it would be really nice to interpret the bias and the loss of information which comes from choosing the structure of the neural network and the training schedule. So for me, that would be the most important part of interpretability. What do you think about it?
So that's a really interesting example. So in that case, I think what you're saying is that we make decisions, often decisions that are well motivated for certain types of regularizations or certain choices of algorithms. And you would like to understand the implications of those choices, for example, in terms of loss of sensitivity. Yeah, that seems like a reasonable thing to do. So, there's versions of this that you can imagine with interpretability that usually in my head, I'm thinking about it as including or not including information, like for SHAP values, like that's saying if I do or do not have a feature, what goes on. But you could imagine doing a similar thing where you're trying to do it with algorithmic choices, that you could say, if I make this algorithmic choice or this other algorithmic choice, how does the performance degrade? So that would be a type of interpretability. And then the question to you is, okay, what are you going to do with that information? If I tell you that I put in a Lipschitz constraint and my, let's say, fidelity, or not fidelity, but the accuracy that I have in doing some classification task decreases, so what? And what is the action that you would take from that information? And maybe the action you take is just knowing that that happened and being aware that that was a trade-off that you were doing, which again is maybe kind of similar to the trade-offs that we have to deal with in statistics, that we just have to make a choice. We can quantify that choice. We can say that what that choice was, but ultimately—
Jesse, but in statistics, it's really easy to quantify. For example, let's take this example of density ratio estimation, which you, for some reason, called likelihood ratio. In statistics, you could do, for example, a kernel method. With the kernel method, you choose the bandwidth, and the bandwidth gives you exactly an idea what kind of frequencies you are suppressing. You will not be able to see high frequency signals with this, right? In using neural network, I do not see a simple analogy to this, and I'd like to.
And you can imagine, though, building a neural network structure where you had an adjustable dial that really was trying to attack, for example, certain frequency modes and see what happens if you were to knock those out. And that would, though, I think you're right, it wouldn't come from a garden variety neural network, but you can imagine building a neural network that had that either high pass or low pass type structure in it. But it would require something different than the typical architectures that we play with.
Transformers.
With
Some types of transformers exactly have that property. Yeah. Thanks. So let's continue, come back to the room. So maybe we'll go here and then there.
Hi, thanks for the talk, Jesse. So I've asked this question of cosmologists, because I'm coming from that side of the room. And so I think we're surrounded by people who work on this in this room, and I think I often feel like there are far too many people working on these problems. But I think we correct me if I'm wrong, we're still sort of in the minority in both particle physics and cosmology in terms of leveraging ML. So you mentioned these sociological interpretability questions. And I've asked this about I call them traditional cosmologists. What do traditional particle physicists want to see? What kind of interpretability do you need to put into your grants to make sure that the person who's the most skeptical, the biggest skeptic, who's controlling the money that you're trying to win, gives you the money, and so such that you convince them that these tools are both useful and understandable. So, which sociological definition would you use for that?
Okay, so I can answer this a little bit just from my own experience. So people know that I was very anti-machine learning, and I am on the record. So when I talk about IFI as deep learning and deep thinking, that was a joke originally that I said at the Boost workshop in Zurich, where I said, look, all of my friends are doing this deep learning stuff, but come on, we're theoretical physicists. We should be doing deep thinking, as if it were an opposition. And so then maybe one way of asking it is, so how did I change my mind? Part of changing my mind was this realization that the likelihood ratio or the density ratio, that doesn't have that I shouldn't expect that actually to be a simple function of interpretable quantities. And so then that realization that whatever I am trying to compute or estimate, it's not as statistically well-founded as I thought. And then some of the work that I did that you call feature engineering, what I would, as a human, write down quantities like these energy flow polynomials that I mentioned, that I said, oh, I have some understanding of their structure. Then someone would point out to me, well, that structure might make you feel warm and fuzzy as a theoretical physicist in terms of how it interplays with certain quantum field theory calculations. But that structure has undesirable correlations with other things, or is subject to these experimental systematic effects, that just because you've written down something that you think is interpretable does not necessarily mean that it satisfies the criteria that you think something good should satisfy. And enough of those examples to realize that basically the framing was not correct. And so where I started to get excited was, wait, maybe I can actually go the other way and say, here are my desirable criteria for an analysis paradigm. let me not try to human derive it. Let me let the machine find that, but let me specify all the things that I want. Let me specify that it's going to satisfy this Lipschitz constraint. Let me specify that it's going to evolve, a certain number of multiplications and such. But I can specify and then let the machine find the optimum. And as long as I put enough specifications in there that make me feel good, or enough regularization, then in some sense I feel better than me writing down something that I can interpret, which may otherwise, not actually satisfy the criteria that I'd like them to satisfy.
Sure. And I guess the follow-up for that was, are you in the minority or the majority? Do the people that you speak to who are not practiced in this intersection, do they buy it? Right? Do they buy your interpretation of interpretability?
Right. So probably the answer, the majority, the answer is no. But I think that this comes to the question of what are we trying to do in fundamental physics? And something that certainly makes people wake up is that if you can, using traditional methods, assess uncertainties, systematic and statistical, on your methodology, and if you can get a better inference in the sense of smaller error bars using machine learning on some quantity of interest to the broader community, people pay attention. With the discovery of the Higgs boson in 2012, I mean, that's machine learning all over the place. But we don't think about it as like, oh, some kind of fancy, we don't think about it that way because we actually feel like the ways that the uncertainties were quantified, that we have trust in those methodologies of validating. And so it might be complex algorithms, but at the end of the day, we have methods of validation. But in some sense, maybe what I'm advocating for is that the methods of validation and the techniques that we use shouldn't be seen as separate. Like we should really be building methods, if we can, to make them as easy to validate as possible.
We have time for one quick last question before the next time. Any takers? Yes.
Definitely not a quick question, but I guess we can continue in the break to talk about it. Do you think maybe some of this confusion about interpretability is because is machine learning on a neural network specifically actually a statistical method? Like,
So
yeah. It's just maybe we're trying to make it do things that it is not designed to do. But I would love to discuss this with people because there seems to be so much confusion.
So let me try to address that. So let's say you're looking at a neural network and you're saying, okay, yes, I have some universal approximation theorem or something, but why that particular functional form? Why do we like having some kind of linear scrambling, non-linearity, linear scrambling? Like, why are we choosing that? And the answer increasingly is that that's not what we're doing, that we're building architectures that are aware of the data type. We're building architectures that allow you to have things like attention mechanisms, which is like outside of that paradigm. We're building architectures that are somehow trying to be better suited to the data structures that we're trying to use. And we could go even further. As long as you can actually take that function and do optimization of it, then we can probably use those in various contexts. And to the extent to which, okay, there's always a question of model selection, which is very complicated for one to get my brain around statistically. And we should definitely talk about model selection. But within model selection, having chosen the model, you're trying to do parameter estimation of the model parameters. That may be, a million parameters, but still is type of parameter estimation. So in that sense, it's high dimensional parameter estimation statistics. It's not easy, but it still falls within statistical framing. I think when we start talking about interpretability, we're actually asking for something different. Interpretability, when we say those words, we're not asking about confidence intervals. We're asking about some warm, fuzzy feeling that we feel as humans that say, oh yes, that looks right. That psychedelic image looks right. But maybe it may be useful for communicating to stakeholders, and it may be useful to communicating to ourselves intermediate stages. But at the end of the day, we would hope that the methods that we're using are based on rigorous science and statistics and not just kind of an emotional response to it. Yeah.
Is it good that we here have to hope that? I mean, it's just, yeah, but I'm just super interested in that. I'm trying to find like good textbooks or to not have to hope that it's based on rigorous statistical methods.
And make it actually, right, so.
Yeah.
So I didn't put this in
I
this.
want to know
yeah.
what I'm optimizing.
Right,
It is, of course, that's why I say it's a big question, but I think,
right.
We might
yeah.
address that in the next topic.
Good. But let me just say one thing. There was a workshop at the Aspen Center for Physics where people were writing on the board, what is the most underused technique in machine learning that should be applied more to physics? And I only half jokingly said linear regression. Only half jokingly. And actually, it's really interesting to think about what are we doing with machine learning that now that we understand a lot about machine learning, could we actually turn them into something closer to linear regression? And I think that actually, as far as making us feel warm and fuzzy on the statistics side, that may be actually the way to go. Okay, with that, thank you very much.
Thank you, Jesse. Hopefully this skips out the bigger discussion. But next, we have our next speaker. So while we're pulling up the top. So connecting with the theme of also understanding failures and problems in different machine learning topics. In this case, we'll have a presentation by Lily Shang from NYU on understanding mitigating failures in anomaly detection from a probabilistic perspective.
Awesome. Thanks so much. Folks this is better? Okay. Is it possible to raise this podium slightly?
No, but you can have distance, it's fine. It works.
Okay, okay, great. Thanks so much to the organizers for having me. Like was mentioned, I'm Lily. I'm from NYU, from the Center for Data Science. I actually don't have a physics background, but I've been thinking about anomaly detection quite a bit. So excited to share some of these learnings with you, particularly with a focus on the recent literature in the ML conference space. Oh, that's okay. So I know there will be many other subsequent talks in this session that motivate anomaly detection. We've already spoken about some motivations in previous tutorials and talks. So I'll just jump right in. I'm going to focus specifically on density estimation based approaches for anomaly detection. And just as this specific example shows here, in an idealized case, if we just had access to the density function of our data distribution, then we would be able to easily say a point B here, which has very low or maybe zero density under this particular distribution, would be considered anomalous. Usually we do not have access to our typical density function, so we estimate it with the model. In the cases where we have high dimensional inputs, such as images, sequences, other high dimensional representations, we have a very exciting toolbox of deep generative models, which allow us to be able to have reasonable approximations of some of these input distributions. Here, I'm just showing some examples of some generations from different deep generative models as early as 2016, 2017. These are models from very different model classes, autoregressive models, VAEs, normalizing flows. But we can see even quite a few years ago, we already had generative models which could create, or rather generate, pretty impressive photorealistic images from these sorts of canonical machine learning image benchmarks that they were trained on. But what if I told you these same deep generative models, when trained on, say, images of fashion, clothing on the left, would fail to detect as anomalous these MNIST digits on the right? How about if I were to say that these generative models trained on images of vehicles and animals on the left failed to detect as anomalous these house number images on the right? In 2019, some folks at DeepMind showed just that across a wide array of deep generative models and architectures. These models would actually assign higher densities to certain out of distribution or anomalous data sets than even the data sets that they were trained on. This empirical result resulted in a flurry of work and response, wondering if maybe we should actually be reconsidering how we perform anomaly detection in high dimensions. We had a whole host of work that specifically sought to understand what likelihood-based anomaly detection meant, there was another whole host of work that actually proposed alternative methods based on the same exact models for anomaly detection. So they would take the same models that showed these worse than random chance failures on anomaly detection in the cases I just described previously, and then change the statistics they were using to score the inputs, show better results, and then suggest, oh, maybe we're actually using these models incorrectly somehow. This whole series of works mostly led to the question of, so how should we be performing anomaly detection? What even is considered the right method to do so? To answer this question, we had some work in response to a lot of this work that ultimately first posed the following insight, that informally, none of these methods can actually guarantee performance better than random guessing without any assumptions on what it means to be anomalous. So just to make this a little bit more formal, we can recast anomaly detection broadly as a single sample goodness of fit test. So we have a single input X, which comes from some data distribution P under our null. Under our alternative, X comes from some other distribution Q. And to perform the test, we have some test statistic of choice. It will map our single example to some scalar score. Any choice of test statistic works. I guess what you would consider the canonical one would be the log density, but substitute whatever function you want here. Now, before I move on, I want to note that we're not even going to consider any potential issues of estimation error. We're just going to sweep that under the rug and pretend we somehow have access to the true data distribution. In other words, all we have to think about is this choice of test statistic here. So say we have some data distribution P, we have some choice of test statistic phi. We then get a distribution over test statistic values for samples from that data distribution. Then to perform our anomaly detection, we choose some threshold based on our decided size we allow for the test, and then we have your traditional anomaly detection approach. Now, what we state in this proposition here is that if you give me some distribution P and some choice of anomaly detection scoring function, phi, I can come up with alternate distributions Q and R, which are different from P, but whose distribution of the test statistic value actually is exactly identical to that of your data distribution P. So what that means is that no matter what thresholding value you choose, you have no better than random guessing. You're incorrectly rejecting your data distribution inputs at the same rate you're correctly rejecting your out of distribution or anomalous inputs. So what's the point here? Basically, what this states is that even though we started seeing these empirical results of alternative ways to use our deep generative models for anomaly detection, these empirical results didn't necessarily mean, oh, there's some better way to do anomaly detection in the theoretical analytical form. To be able to state that one method or one choice of test statistic is better than another, you have to actually make a further assumption on what are the out distributions or out distributions of interest, or rather what is considered anomalous in your setting. Another way to describe this is that different test statistics imply different relevant out distributions or anomalous distributions. So when we perform detection based on likelihood or just density in general, what we're stating is that we have power to detect stuff that is low density under a given parameterization. So if that is indeed what it means to be anomalous in your setting, that this test is a good test. If we're performing detection based on a likelihood ratio, which is also a common approach, we are now specifically specifying some base alternative distribution. And if that is indeed the distribution of anomalies of interest, then we have our uniformly most powerful test, but otherwise we are explicitly making that assumption. It's not necessarily the uniformly most powerful in other settings. And then we can encapsulate all other possible statistics we might consider for performing this detection. And to be able to justify that statistic, we then need to justify our definition of anomalous. Okay, but we still haven't dealt with this issue that sometimes these other statistics just work well empirically. How can we understand what's going on here? To do that, I'm going to walk through a quick example that was pretty prevalent in the machine learning world. We call this the typical set hypothesis, but hopefully this helps build a bit of intuition and color as to what is going on. So here's a different test statistic, one that we haven't seen before. Instead of looking at the log density, it's looking at the deviation of an input's log density from the average log density of your training data. What this means is that now we're not just going to be flagging low density points as anomalous, but we'll be flagging deviations on either side, low or high, as anomalous. This was justified in the literature by drawing an analogy between high dimensional image distributions and a high dimensional isotropic Gaussian. So in particular, when we do have a very high dimensional Gaussian, the highest density region is near the origin, but the vast majority of the probability mass lies in a thin annulus a certain distance away from the origin. And folks were suggesting maybe in some of these image data sets, such as the CFAR10 data set of animals and vehicles, we actually have certain other image data sets, such as the data set of house numbers, which happens to live in this high density region of the support of this data distribution, but ultimately has very low overall probability mass in this distribution. This might sound potentially plausible, but the one problem with this whole story is that now we're assuming a lot of things, namely that we have these image data sets that are overlapping in support in all sorts of different ways. I can go into the problems with this particular assumption and the consequences it implies, but maybe I'll just go to talking about a potential alternative explanation, which might make a little bit more sense. So recall we saw some phenomenon in our deep generative model. Namely, we saw that certain out distribution or anomalous inputs were being assigned higher densities than even the training inputs. Now, because these generative models are an approximation of the underlying data distribution, we either have that the same phenomenon exists in the data distribution, or it's due to model estimation error. The model is placing probability mass where it shouldn't. Now, if we actually think about these images in discrete space, which they are represented as discrete, we have probably the fact that you would never expect to draw a house number from the data set of animals and vehicles, even in infinite samples. So it's more likely the fact that these distributions actually do not overlap in support, and we have an issue where our deep generative models are placing probability mass where they actually probably should be placing no mass. So then what's happening with all of these alternative methods of using the same models that are getting better results on these particular benchmarks? They're probably actually just correcting for this particular error. So to understand in the context that we just described previously, if we know that our models happen to assign high density to certain inputs that they really shouldn't, much higher density than they even assign to their training data and training distribution inputs, then if we just said that anything that has too high of a density under the model is out of distribution, we will be able to capture those anomalous inputs when we wouldn't have otherwise with a likelihood-based test. So you might be wondering at this point, how is all of this happening, all of this convoluted explanation for what's going on, when we have generative models that are presumably good? Don't they seem to be generating pretty photorealistic, pretty good quality images? And my response there is that you can actually have very minimal estimation error cause detection failures as drastic as the ones we're seeing. So just to make this more clear, say we have we're in discrete space now, just to keep things very, very simple. Say we have some true distribution that's supported on just a subset of the overall sample space. And now we're going to create a model. So this is I guess, a simple toy example proof by construction. We're going to create a model that is very close to our true distribution, but all we've done is move a slight amount of probability mass away from each of the individual in-distribution inputs onto some small out of distribution region of this sample space. Here's our misestimated model. And the result is that almost all of the probability mass still lies in the in-distribution support. But what we did was we moved enough mass and concentrated it in a small out-of-distribution region that for every individual element in our out-of-distribution region, we actually have a slightly higher probability than any of the in-distribution elements. Once we do this, we can play around with relative volumes between our in-distribution data and our out-of-distribution, or sorry, our in-distribution and our out-distribution. And what ends up happening is we can have very good likelihoods for our misestimated models. Our misestimated models will nearly always be generating exactly the points that are in the data distribution itself. But here now we actually completely fail in out-of-distribution detection or anomaly detection broadly. So what we've seen now is that generative models can exhibit some pretty bad failures for anomaly detection. It's possible to potentially deal with some of these issues post hoc by applying a different method on top of the generative model that takes into account its form of estimation error. But is there something else we can be doing? Can we maybe, rather than playing this whack-a-mole situation, try to deal with these further upstream in the process? To maybe get to make a bit of progress on this front, the first thing that's useful to note is that when we're looking at likelihoods, generative modeling is very hard in that we have to try to approximate all parts of this very high dimensional distribution. And likelihood itself does not necessarily prioritize the bits of information that we actually care about for detection. That would change between what we know and what is novel. Maybe to make this a little bit more concrete, if we're, say, looking at the entropy of this joint distribution that we're describing based on our semantic information y, and then all of that other information that makes something an image x, we have actually very little bits of information that just would be used to distinguish between the classes that we already know about, whereas all of that other information that makes, say, something look like an image just takes a lot more effort to get right. So how might we counteract this issue? Maybe we might want to consider not forcing our hand and forcing a generative model to be the solution. Maybe we should be actually figuring out what parts of our high dimensional input distributions we should actually be prioritizing our modeling. In the canonical machine learning approach, the first thing people turn to is representation learning. So I'll just talk about how we might be able to start using representation learning for this particular objective. So then what constitutes a good representation in the context of anomaly detection? Well, we had already described that we probably want the information that would distinguish known classes, given the assumption that that sort of information is what would help detect new classes. So very simply, maybe we might want to just consider the representations that allow us to predict our known classes from each other. Previous speakers have already mentioned this a bit now, but we also want to make sure that we're not taking into account spurious signal that just happens to be correlated with these semantic class labels that we have. And the first thing we can consider doing is just simply breaking that dependence between our classes and then Z, whatever we are calling this spurious signal. To do that, what we're going to do here is we're going to just define an alternate distribution, which we can actually derive from our current data distribution, where we specifically broken that dependence. We can do so by reweighting, balancing, various approaches such as that. But this alone doesn't actually necessarily guarantee that our representations won't contain that information anyway. It's been shown in the machine learning literature that actually oftentimes, even when we are doing things such as balancing various approaches to deal with robustness to spurious correlations, that the representations actually still contain the information. It's just that last linear layer that's not taking that information into account in the actual prediction. So if we want to actually deal with the representations themselves, we can just add an additional constraint here. Here I've imposed two additional independence constraints. One is just so that our representations should be independent of Z, and then the other, that our representation should be independent of Z within each of the classes. Here's just definitionally what we mean by independence. the joint being the product of the marginals. And as for how we might be able to start trying to impose this constraint, we choose to use a particular mutual information penalty, various ways to, various mutual information estimators you could consider. We consider using a density ratio approach. This is just a very high level summary of what I just described in the past few slides. Main thing to note at the very bottom is now we just have some objective that describes what we mean by, say, a good representation. Various ways to do, various objectives we could describe, various ways we could optimize for this objective. Here's the approach we take. We first compute weights to perform that reweighting to get that distribution where Y and Z are decoupled. And then we actually seek to learn the conditional of Y given R of X, and thus the representations R of X in this bi-level optimization. What happens here is as we're taking each gradient step for our classifier, we're learning a critic model to be able to approximate the mutual information. This is all just the density ratio trick here. I'll probably just move faster here. And then once we do that, we add that as a penalty to our loss function and optimize accordingly. So as I've mentioned before, I don't have a physics background, but I have had the pleasure to working with some other folks who are in the particle physics world. And we've applied some of these ideas to anomaly detection with the HS4ML data set. What we do here, we've described this approach as multi-background and nuisance-aware representation learning. But really what we're doing is kind of what I've described previously. The main innovations here relative to what I understand to be some of the main approaches today in anomaly detection are that one, we're actually taking into account all of the different known backgrounds when we're doing the when we're doing modeling itself. So whereas I understand oftentimes we are modeling just QCD when we're doing some of this anomaly detection, here we're actually learning representations by taking into account what are exactly the features and information that help distinguish jets from each other, rather than say just like the information that represents what it means to be a jet. With this approach, once we have representations, we can apply all sorts of functions on top of these representations to perform our anomaly detection. Notably, we can also perform generative modeling on top of the representations. We actually find that doing so with maybe the most simple generative model you could consider, just class conditional Gaussians, fit a Gaussian on top of each of the individual representations for each of the jet classes. We find that this actually performs quite well, better so than, say, fitting a generative model directly on top of the input distributions. Multiple reasons why this could be such. We've talked about how prioritizing the information that we want can be important. Also utilizing as much of the jet data that exists to help with modeling can also be helpful. And then what we get from the robustness criteria that we described is not only the same sorts of robustness that we're seeing in a lot of the anomaly detection approaches in high energy physics, but also we're explicitly enforcing these constraints for each of the individual jet classes. So at a very high level, what did we go through in the last 25 minutes or so? Ultimately, generative models do exhibit detection failures, and there have been some pretty notable ones that the machine learning community has noticed. Oftentimes, this has happened when the data distribution that you're interested in happens to be made of inputs that are generally more complex than those of some anomaly distribution that you would hopefully be able to detect. Once we start to play around with relative volumes, which makes a big difference in high dimensional inputs, then failures can result from even small amounts of estimation error. We can apply post hoc test statistic corrections that will improve anomaly detection by taking account this estimation error. But ultimately, what it means to do the correct anomaly detection really depends on what you mean by what is anomalous. And then if there's any one takeaway Here, it's that generative modeling is hard. Maybe consider taking into account outside information to really help with learning good representations to build models upon. That's all I have, actually. So happy to take any questions from here.
Thank you very much for the fascinating talk. Let's see if there are questions. Let's go first here and then Jesse.
Hi, thanks so much for the talk. I mentioned this briefly yesterday, but I didn't get into it. But I think you might be close by these guys. So Goldblum et al. Put out this paper where they talk about sort of an information theoretic approach to, so why does machine learning work the way it does, right? Do you find, have you looked into sort of in this CFAR or the MNIST example where you say, okay, does the subspace of house numbers live inside the cars and trucks and elephants distribution? Do you think could the structure, so could the number of bits of the structure itself have to do with anything, like the actual structure, the images itself, the fact that you're feeding them in as images? Could the fact that the images are far more structured than, you know, uniformly drawn data contribute to that misclassification, misidentification?
Yeah, great question. My sense for some of these failures that we are seeing are indeed that kind of this rising tide lifts all boats. By developing these inductive biases in these models, which allow us to better model images, we're better modeling all of these images, anything that looks like a natural image. And oftentimes what ends up happening is you see examples where regardless of which image data set you have trained on, all of the images which have, say, like a shorter compression length than the images of the data set that you have trained on, they happen to have higher densities than others. So it's not specifically SVHN and CFAR10. These pairs just happen to exist because those are the ones in the original paper, but people have kind of shown this trend more generally.
Yeah,
Yeah, no problem.
Thanks, Lily, for the sobering lesson about anomaly detection. I want to understand just how bad it is. So let's say I'm going to change my goal, and instead of having to identify individual anomalous objects, I'm going to change my goal and say, all I want to know is what fraction of my data set might be anomalous. I'm not sure if I want to think about upper bound or lower bound. But if I change that, that is, I'm willing to make mistakes object by object, but I just want to have some robust estimate of what fraction of my data is out of distribution. Do I have any hope of maybe being saved from your sobering realization?
Great question. I haven't thought specifically about the fraction case, but I do know, for instance, once we move away from single sample to batches, then we're back in your typical goodness of fit testing world, and then we have lots of guarantees there. As I'd have to think a little bit more about your specific question, but my intuition is that hopefully we lie somewhere in between.
Okay, thanks.
Yeah.
Right. So let's go next to Lucas, and then we'll go back there.
Yeah, thanks for the great talk. Yeah, I think kind of in relation to particle physics, the main thing that we've been grappling with is kind of the one on the lower left, that kind of there's no kind of by definition, no kind of general purpose anomaly detection algorithm in the same way that there's like no universal most powerful test in the most general way. So, but the thing that particle physicists want to somehow get around with is kind of explicitly specifying an alternative, but at the same time, I mean, you make the point that it's important to at least somehow conceptualize what alternatives could be. So just curious, like in statistics, are there some ways to kind of think about specifying a family of alternatives without kind of explicitly specifying like a generative model for these alternatives?
Yeah, so one approach, for instance, is choosing the parameterization by which you just perform likelihood-based detection. So I guess in the case, one thing that I didn't describe previously is that when we are learning good representations. Ideally, if they have encoded our inputs in a space that actually does represent semantically, closeness in these in this representation space does semantically represent closeness in the way that we care about, then we're in a better spot than just, throwing up our hands and just choosing whatever arbitrary representations we would like. As for other ways to deal with this besides actually just, likelihood ratio tests, specifying your alternative in particular. One thing that is worth noting through all of this is that in the particular proposition that I do have, we have made the least amount of assumptions possible. We just said that Q could be anything that is just not P. And typically that's already, people are already making assumptions more so than that. Oftentimes it's something like, I don't know if I can speak to the particle physics world, but say for other anomaly detection tasks for other sorts of data, you probably can already rightly assume that the stuff that will be anomalous will probably not overlap in support with, say, a data distribution that doesn't have full support, something like that. So some of these things we will get for free. I don't know if the same thing can be said about this particular application, but hopefully that's insightful.
Yeah, thank you.
Thanks for the talk. I was just thinking again about what you mean by anomalous when you say that the house numbers, for example, are more anomalous than the training set. Presumably that means that the training set, the images in the training set are less likely to be generated under the generative model than say a house number, which is fair enough. But that just seems to me to kind of indicate that the distribution you're using is a little bit different than the training set, and maybe the training set isn't really relevant. Why isn't that? Why can't you compare your house numbers, say, with pictures that are generated from the generative model instead of the training set?
Oh, that's a great question. So that's done too, and often we see the same results.
Some more questions here. Yeah, we have time. We still have 10 minutes, so wait. If we run out of questions, we'll go back to Jesse's.
Hi, thanks for your talk. It was very clear. I was wondering about this detection failures due to the complexity of the model, and if there's specific methodologies, because it might be a very naive question, where you know whether the method it fails because of the complexity inside your method or because of bad input data. Because, for example, with the pictures, if you have training data which is only white men and you try to identify a woman of color and it doesn't recognize what that is, this is an example from social science, there obviously the problem was the input data and not the model. So especially in anomaly detection, I can imagine that in the end you're going to set a limit somewhere on the likelihood that there is something even though you didn't find it. And then you kind of want to know whether you just gave it the wrong inputs or whether your method has some sort of uncertainty on it. So, yeah.
I'm not 100% sure I understood the question. So if I misunderstood, feel free to just follow up. My current interpretation is that you're asking, when do we know it's a problem with the model versus the data? At least in all of the analysis that I've done here, we're just assuming that the data is as is and that our model is trying to best represent whatever data distribution we do have as well as possible. So then in the, if the question is more about like this debugging sort of thing, here we actually just have all of the data from our in distribution images. And when it comes to seeing if the problem is complexity based or some other problem based, everything here has been canonical data sets from our very standard machine learning benchmarks. So none of this work has had any bearing on better understanding the sorts of data that are going into our models. Definitely take that as a reasonable thing to think about.
Okay,
Cool.
thanks.
Hi, very interesting talk. I have a very simple question. On slide 24, you started talking about these spurious signals and trying to be decorrelated to them. Could you elaborate a bit more what you mean by these spurious signals?
Yeah, so in the case of an image, a spurious signal could be, say, the background of an image when you actually want to be detecting what animal is in the foreground. In the context of particle physics, if we're trying to ultimately do some aggregate statistical analysis downstream based on a search variable such as, say, invariant mass, and we don't want our anomaly detection based approach to just rely on the invariant mass, then Z would be invariant mass.
Okay, thank you.
Any other questions here or on Zoom? Bob?
Sorry, I was trying to raise my hand. I'm trying to find the thing. I don't know.
Someone else?
Oh, Kyle has a question, so maybe we'll go. Kyle, why don't you go next?
Great. Is it okay? I can wait.
Well,
I
I'm
just-
sure yours is better.
Should I go ahead? Okay.
Go ahead,
Go ahead. Yes, go ahead.
I mean, it's a kind of semi-vague question, I guess, but it just seems like there are a few things that are kind of different ways of looking at the same problem, sort of like what is the unknown you're solving for, in the sense that the sort of impossibility result that you showed, you know, you have that there. So, you know, one way is to specify an alternative, and then think of like the tests that follow from that alternative. You know, another way is to somehow just pick a method or like regularize in some way, which basically gives you power for some alternatives and not for others. So it's like the same thing, but kind of switched around what input you're providing and what the consequences are. And then a kind of variation of that is this, I guess, sort of the slide that you have up now about the choosing the representation, which I guess is sort of like the regularization issue, but not exactly the same. I'm just wondering if you think there's like any hope, or if you've seen any kind of signs of something along a theory that would allow you to kind of relate those different things in some more like effective way. Does that make
Yeah.
any sense what I'm saying?
That's a great question. I haven't seen anything in the literature so far, but at least conceptually, the way I've been seeing it is we have this overall pipeline, we have some data, which is our input data, and then we're going to train a model and then perform anomaly detection. At any stage of that pipeline, we could spend our effort. Obviously, if we just could build even better generative models that say don't have these particular natural image biases that they do, maybe we would already be able to deal with some of these failure modes. Doesn't necessarily mean there might not be other failure modes that we don't know about that may come up. But right now, I only see it not in a theoretical way, just conceptually, that we can tackle any part of the pipeline. And I would be curious to see what. So one thing that I can actually mention before I close is that oftentimes there's probably a bottleneck at every stage. Like for instance, if you were to have a bad generative model, then you can only correct for it so much unless you were to actually be able to know of all of the issues with the generative model. If you have an input representation that has lost information that you actually need, then you can't recover it after the fact. But then beyond that, my sense is that as early on as we can improve our results or limit the bottlenecks we have, the better. Besides that, would be really interested to see if folks can kind of connect these ideas better.
Thank you.
I hesitate. I'll get to my question in a moment. My comment is we seem to have circled back to Neyman Pearson versus Fisher, and then Neyman and Pearson said specify an alternative, take the likelihood ratio. Fisher because he didn't like naming, maybe said, no, just you need some vague idea of which direction your alternatives in. But it's been known since all of them that if you didn't say anything about the alternative, then indeed you can get any answer you want. And this is the second workshop where I've been surprised that people use the density, the single density, to detect anomaly, because you use if you switch from x to f of x, you have a Jacobian, you can put the peak anywhere you want and put the low density area anywhere you want. So I guess most of what you said made sense to me, but then when you get to the numbers, now I get to my question. Given all that, when you think about the numbers and the pictures, the cats and whatever the pictures, is there any way my comment could be relevant at all? That is it possible that in some space somehow it must be going on that there's a likelihood ratio in some space that's picking out the numbers, because that's just the math of the Neyman-Pearson lemma. So is it helpful at all to think about it that way?
So one thought, I definitely take your point about being able to take some invertible function, change of variables, then we kind of have, we can have densities that look however we'd like. In the case of images, and often probably many, I guess, canonical machine learning benchmarks we do have, I think it's reasonable to assume that some of these distributions are indeed discrete, or many of them are actually even modeled as discrete. The images themselves are only represented in RGB pixel values of 1 through 25, the integers, 1 through 256. In that case, then we no longer have this problem with the parameterization. We actually probably do have a situation where we have one distribution that's supported on one subset of the space, another distribution supported on a separate subset of the space, and our models are just placing probability mass everywhere.
Thank you.
With that, I think we're going to thank our speaker. Thank you very much, Chloe, and our several guests. Fascinating questions, fascinating discussions and insights. So I think next we have coffee break. We can continue. We're back at 4 o'clock. Yeah. People who wish to start a poster tonight or tomorrow, leave your poster up during this coffee break on level 2. See Danny and Paul and Theo.
Okay, let's have a seat, please. We're going to start. So we have 4 talks this session, so we'd like to get going. Our first talk this afternoon is by Gaia Grosso on statistical tests for anomaly detection in particle physics.
Thanks, Bob. All right. I guess I can start. So hi, everyone. So as Bob just said, my talk is going to be about statistical tests for anomaly detection, in particular for particle physics, but probably most of the things I'm going to say, they're going to be even more general. So what is going to be about my talk? I will try to give you an overview of how do we use machine learning for statistical tests, in particular in the context of the LHC. I'm going to try to point out what are the challenges of performing statistical hypothesis tests or statistical tests for anomalies using machine learning, and provide some solutions or ideas for possible solutions to these topics. As a disclaimer, yeah, I'll just say that part of the example we're going to show are based on my own research, but yeah, I'll try to reference also many other interesting works that I found in the literature. So moving forward, I want to start, first of all, by just giving like a definition about anomaly detection, just to be all on board, because we've heard from Lily already about anomaly detection before, and she explicitly talked about out of distribution anomalies. But when we think of an anomaly more in a broader sense, we just define an anomaly as a pattern that in data that do not conform well with the notion of normal behavior. And this could be something that is an out of distribution point, something that we've seen in Lily's talk, but it could also be some effort that shows up as a distortion in the statistical behavior of our data. So in that sense, we can also think of collective anomalies. And the objectives, the goal we have by performing anomaly detection in particle physics and in general in science is to, first of all, detect such anomalies, but also to assess their statistical significance. That's also something crucial for scientific discovery. So there are multiple situations, I would say, in the context of LHC in which we can think of using anomaly detection tools to solve, let's say, practical problems. And they usually kind of reduce to like all these situations where we are trying to understand or to answer the question, how well do we understand our data, or how good are our models, our physical models for our data. And this happens, for instance, where we are in very different stages of a typical pipeline of a LHC experiment, starting from the detector readout, when we are trying to understand if there are hints of detector malfunctions. And in that context, we do data quality monitoring, and many times we just don't know what is the source or what's the nature of a malfunction or something we don't really understand in the data taking. And all the way down to the final stage of our experiments, that is the offline analysis, where we might ask ourselves, is there any hints of physics beyond the standard model that we have not thought about yet? But the questions about, let's say, anomaly detection and how well do we understand our physics model also go to the side of the simulations. So we use simulations all the time in our daily basis as a scientist, experimentalist at the LHC, and we ask ourselves most of the time, how can we trust our simulations, or how good is a new surrogate model with respect to a ground truth of full simulator that is based on physics rules. And these kind of questions, they are becoming more and more relevant nowadays with the use of generative AI. So this is a topic that is relevant for physicists, but is relevant for computer science as well. And anomaly detection is a tool that can be used to validate simulations. And even before starting my talk, or as a, let's say, introduction, I also want to go through 3 slides about terminology. These slides kind of came up after I talked to Lily a couple of weeks ago. And we were trying to understand what do we mean by anomaly detection from this different, let's say, perspective as a computer scientist, as a physicist. And if you ask to a computer scientist what anomaly detection is, or how do you do anomaly detection, they will always say to you that there are three, let's say, big branches of applications or approaches that are supervised, semi-supervised, and unsupervised techniques. And when they talk about supervised techniques, Lily said something already before, they refer to the situations in which a signal is known. So we have a notion of what the anomaly should be, and the challenge is how to detect it. And this is our, let's say, typical scenario at the LHC when we are performing a signal targeted analysis. And the traditional way we solve this kind of problem is by performing a hypothesis tests, usually the likely ratio test. And there is a lot of challenge and a lot of machine learning being used to, let's say, optimize our data selections and our summary statistic construction in order to make this the best, let's say, or to make our analysis optimal. But we kind of know how to do this, or there is a lot of, let's say, a lot of effort ongoing over there. So when we actually think of anomaly detection from the physics point of view, we are more like we are considering more the problem of a semi-supervised approach. So a situation in which the signal, an hypothesis for the signal is not given, and we want to understand how to test the data for, or how to test our model, our standard model, as a goodness, as a good representation of our data. And this can be done, as also Lily mentioned, by performing a goodness of fit test rather than a hypothesis test. That it turns out to be also a two-sample test in the end. And in this framework, we've given just one hypothesis. That's the reference hypothesis, the null hypothesis, which is usually the standard model, but could be also, for instance, the nominal behavior of a detector, if you're thinking of data quality monitoring kind of applications. And then we've been given the data. And usually, I mean, if you perform a goodness of fit test, you have been given this reference model in an analytical form, in a closed form. In most of the time, in physics application at the LHC, we don't have any information about our standard model or our nominal distribution of the data in detectors in a closed form. And therefore, we need to replace this information with a representation of the model that is given by some sample that we could call a reference sample. And when we do so, we essentially turn the problem of goodness of fit into a two-sample test. And that's where we usually think of applying machine learning to solve the task. I wanted also to just briefly give a comment about unsupervised techniques. We see unsupervised techniques mainly based on mainly targeting clustering or self-organization of data to build good data representations. Lily already mentioned how essential it is to have a good data representation in order to perform successful anomaly detection. The comment I wanted to make about supervised techniques is that they alone cannot really give us a way to assess the significance of an anomaly. So we should always follow an unsupervised approach to data analysis or data exploration with a semi-supervised or supervised method that is able to give us some notion of statistical significance on top of it. So this talk is going to be mainly about this second category I've talked about. So goodness fit or even more two-sample tests. And two-sample tests for anomaly detection at the LHC. What do we do to perform two-sample tests at the LHC? I would say that one of the most common way of attacking this problem using machine learning is to perform a classifier-based two-sample test that can assume very different, let's say, forms, or can be set up in very different ways. But in general, all these different approaches, and I'm going to talk about some of them right now, they all essentially end up providing a good approximation of the log density, the log ratio of the densities, something that Jesse also mentioned in his talk. And once you have this information out of a classifier, you can think of using this information to build a test statistic. So there are many ways you can do it. A standard way one could think of using a classifier to perform a goodness of fit or two-sample test in this case is by using the one-dimensional output of a classifier, essentially the classifier score, as a summary statistic on top of which you can run all the standard goodness of fit tests that you are aware of, like Kolmogorov-Smirnov, Anderson-Darley, chi-square. But you could also think of using metrics that are more like based on the classification scores or the goodness of the classification, such as accuracy, AUC, or misclassification errors. Or one could use or could think of using the whole density ratio itself to build something like a normal Pearson test that we have talked about a little bit in the discussion after the talk of Lily's. And in that case, you could think of really use the estimated density ratio to build a likelihood ratio hypothesis test, where the alternative hypothesis is this parametric hypothesis that comes from the classifier models. But you can also think of using a classifier just as a mean to select some interesting events in your data, for instance, the ones that are high score in the classifier output, and use them to enhance some prior signal hypothesis. And that's something that, for instance, has been done in many ways for enhancing resonance anomalies and performing bump punting in a more in an enhanced way. So these are all options. What is really important to kind of remember is that once you have defined a test statistics, you're not done. It's not the end of the day. You also need to make sure that your test is calibrated and that you control the rate of false positive. And this can be done essentially by building a distribution of the test statistics under the null hypothesis. And you could do this by bootstrapping or making permutation tests. There are a bunch of different ideas. I recommend always to look at a paper from Chakravarti and Kusela that I point here, where they discuss about different ways you could build null hypothesis for goodness of fit tests. And that's really crucial in order to make sure that our evaluation, our metrics are under control and are robust. But so what I said so far is like nothing very complicated. It's just training a classifier and use it to kind of reduce the information of a multidimensional space down to a one-dimensional space, and then use these projections to essentially define a test statistics. But so where is all this challenge coming from? And the challenge comes from the fact that our setup or the problem we are trying to solve are in general hard. That's because we have big data sets with high dimensionality and large sample sizes. And in these big data set, anomalies are really rare. So we expect the two data sets we're using in the classification task to be almost identical, and the anomalies being something like a very, very tiny fraction of our data, or even almost absent, essentially. And the other point I wanted to make is that conversely from like standard application of goodness of two sample tests in, let's say, computer science applications, where, for instance, we are thinking of finding pictures of cats over pictures of dogs or these kind of things, we don't really have, in particle physics, we don't have a way to intervene as humans to correct for false alarms, in a sense that we cannot just look at one anomalous event and by eyes understanding whether the model made the right choice or not, and then correct for that. And that's essentially why you need to develop statistical frameworks that are robust and that we can trust in order to claim anomalies in particle physics. So what are the challenges? I'm going a little bit more deeper into this topic about statistical anomaly detection, in particular at the LHC. I try to kind of summarize what I think are the main challenges of performing anomaly detection in a statistical way at the LHC by like pointing out three main questions. The first one is, how do we design this test, or a good enough test? The second one is, how do we propagate systematic uncertainties in the reference model? Because I forgot, I think, to mention it in the previous slides. that one of the other features about our data is that our models are affected by uncertainties, and we do want to include this information and be aware of this information when we perform anomaly detection. So how do we propagate systematic uncertainty in the reference model? And finally, but not less important, how do we make sure that our data are informative about existing anomalies? We heard from Lily about the problem of data representations, and essentially I'm going to try to comment about this a little bit at the end of the presentation, if I have time, hopefully. So I'll start by commenting about what does it mean, or how can we make a good design for two sample test for anomaly detection. And essentially, what we need to keep in mind is that when we define a two sample test based on a classifier, the choice of the models that the architecture essentially and the regularizations that we use for the training task and that define the final results of our model are in some way biased in the results of our test, and essentially defines a family of hypotheses, of signal hypotheses to which the test is sensitive to. And the question is that, is there a way to make it robust or make it less dependent in order to capture any possible signal that we are not even thinking about to start with? And the answer is that, and we've said this already multiple times today, that there is not an optimal or a unique optimal solution to the problem of anomaly detection. So we will never find one single model that will be uniformly able to capture every possible signal. And we can see here an example by looking at these power curves that I show here for different signal injection over, and this is the LHC Olympics data set. And what I'm showing are power curves for BDT binary classifier with different choices of hyperparameters. And you see that, for instance, the power, the model that performs better with this signal injection of around 300 signals events, that is the orange one here, is actually the one that performs worse when the signal injection is way lower. This tells us that if you think of using, for instance, one signal benchmark as a way to tune your model somehow, such that you have like some satisfying architecture or training procedure to apply, you might be making a big mistake, and we cannot foresee this. So can we do something to prevent this kind of problems, or can we mitigate this kind of problems? And one thing we've been thinking with Marco Letizia, that is here in the audience, and I invite you to talk to him about this topic later today. It's also mentioned in the poster he's presenting this afternoon. But one thing we've thought about is performing multiple testing. This somehow sort of answered also the question that Igor made during Jesse's presentation about multiple choices of hyperparameters and interpretability. But yeah, what we tried to do in this case was taking as a model or a family of models a kernel-based model. So it's a mixture of Gaussian kernels. And we focused on the hyperparameters that defines the width of the kernels, that here I called sigma. And we've looked at how the test statistic that we defined as a Norman-Pearson test varies by changing the value of this sigma. And what we see, and this is also intuitive, is that if we take a very narrow width for our Gaussians, we become sensitive to low scale effects or fluctuation in our data distributions, while when we take a broader width for our Gaussian, we become sensitive, or we are optimal for detecting kind of a departure that is a broader range. And what we try to do is performing multiple tests, performing all these tests and combine them or aggregating them by inspecting different means of aggregations at the level of the p-values of the single test. Here I, for instance, show a power curve for an aggregation that is based on the minimum of the p-values. And what we saw, and by performing several experiments over different signal injections, different kind of injections, is that by performing multiple tests and taking an aggregation, we build a test statistic that is better on average on a wider range of possible signal injections, while not doing let's say the sensitivity dramatically in any of these cases. So this is a way one could think of mitigate these kind of issues. And there is another, let's say, topic I want to talk about when we're talking about designing the test, that is interoperability. Is kind of convenient that Jesse gave his introductory talk about interoperability just before our session on anomalies, because this actually connects a lot with what he also commented about, that is the fact that when we think of designing a model for improving or making the best sensitivity reach, it doesn't really necessarily mean that you're building the best model for interoperability. But when we are performing anomaly detections, in the end of the day, we want to have not only a statistical and robust framework to make sure that the anomalous or the alarms that we raise are significant, but also we want to have a mean to interpret what's going on over there. So why do we see, why our algorithm is returning an anomaly alarm? And the question is, how can we make a model being interpretable without biasing in towards any specific signal hypothesis? This is a question that cannot be really answered because it's kind of ill-posed, in the sense that in order to make a model interpretable, we need to make some assumptions about some specific functional forms, but one can think of making these assumptions the less, say, impacting and the most general possible, such to provide a family of universal approximators that can be interpreted without losing in expressivity. And something I've been working on lately that is not yet finalized, but I wanted to quickly flash a slide about it, is using, again, Gaussian kernels or kernel methods, but in a sparse regime. So the idea is that we take a linear combination of kernels, of Gaussian kernels, but this linear combination is over a small number of kernels. What we do in order to ensure that the expressivity of the model is good enough is that we allow this kernel to learn the location, the optimal locations. So the idea behind this choice is that when we are looking for some tiny departures of a reference model or a reference distribution, or our data from a reference distribution, we expect these tiny departures to be localized in some specific region or very small. So it doesn't require too many degrees of freedom to be expressed or to be described. The problem is how to direct the few degrees of freedom in the right region of the phase space. So the idea here is that we could think of having a really small model, but with the flexibility or the adaptability such that the degrees of freedom can be attracted or can be pushed during the learning task towards the regions that really are relevant or they show relevant discrepancies. Okay, I'm gonna go very quickly about the second topic that is actually, again, related with interoperability, which is about quantifying uncertainties. So we've seen now like all possible ways one can think of mitigating the problem of model selection for, let's say, managing to grasp any possible, let's say, data distortion that we might not even think about. But then we also know there are some, like there is a family of, let's say, of distortions that we are aware of and we don't want to be sensitive to. Those are those distortions that can be modeled by nuisance parameters, and they define essentially a ballpark around our reference model that is our uncertainties error. And so at the LHC, in the frequencies approach or the standard approach to solve this problem is introducing nuisance parameters and modeling this distortion via nuisance parameters. And we inject this, let's say, a new set of parameters in our likelihood ratio hypothesis test, and we profile over them. something I've been working on in the past years, and I already presenting at PHYSTAT many times, is a way to include the same kind of formalism in an anomaly detection or a statistical anomaly detection task. I'm gonna go quickly over this because I think at least half of the audience already saw some of these presentations, but the main idea behind this is that we want to parameterize the data distributions as a reweighting of our reference hypothesis. And this reweighting is made aware of the family of distortions that capture systematic uncertainties, and this family of distortion is parameterized by nuisance parameter. So we have this term here, this ratio term here that encodes possible distortions of the data distributions that are allowed within uncertainties. And the second term here, this is it could be an error network with any universal approximator. It's instead a term that is free of capture any other additional residual anomalies on top of the distortions that we are aware of. And by using this parameterization, we can essentially solve the problem of maximum likelihood that I showed you before, as the difference between two terms, where essentially the systematic effects get cancelled and the surviving ones are the real anomalous features. And yeah, you can use this to essentially solve the problem in a very standard way by checking and calibrating your test statistics and making sure that is independent of the set of nuisance parameters. Yeah, I want to make a comment about data-driven techniques. So, and we also have ways of performing anomaly detections in which this reference distribution is built from data. And this is like the pros or the advantages of this approach is that you can get rid of many of the systematics, but there is still like, let's say, two cons. The first one is that you need to make an assumption on a signal region. So that's essentially telling you that only a specific family of signals is allowed for the search. And there are still uncertainties coming from this transfer function that need to be dealt with. I will quickly, like in very few minutes, since I'm almost done with my time, say something about building data sets that are informative. And that's something really relevant at the LHC because we have this very complex pipeline given by our experiments where we collect data 40 megahertz and we have to reduce all this information down to just 1,000 hertz of data and then build summary statistics that are almost like they're low dimensional up to one dimensional view. And doing this sort of induce clearly a bias on what we are able to detect. And the idea recently has been trying to reduce this biases by, for instance, changing our trigger, replacing some standard triggers with the clever triggers based on anomaly detection. And I think Thea is going to talk about it. And you heard something about Axel Little at CMS already yesterday by John's presentation. And yeah, we can also think of performing analysis essentially online or triggerless. And these are things people are looking into. Yeah, I'm gonna skip for lack of time. Yeah, you heard already from Lily the relevance about data representations and building embeddings that can capture anomaly detection. There are works ongoing about this, and the question is how do you make these embeddings, let's say, anomaly preserving. Yeah, so I just quickly close here. Yeah, the last part of this talk is more like ideas or topics people are thinking about, and happy to start a conversation about it. But I wanted to close just by pointing out some personal thoughts on the topic. So I really think AI has the potential to extend anomaly detection beyond the human abilities, but it's not a free lunch because it's always trading some assumed knowledge for a richer basis of acquire experimental evidence. So it's really essential in order to make these AI tools useful in scientific discovery to build a rigorous statistical framework. That's the reason why we are all here today, I would say. And there are a lot of, let's say, challenges at the LHC, and these offer like a very rich playground, both for statisticians and computer scientists to develop ideas and to challenge themselves with very structured data, both thinking about interoperability, data compression, data representation, and also uncertainty quantification. So I think we should really embrace this opportunity to have knowledge transfer between our communities and build something novel out of it. Thanks.
Thank you. Well, you know you're not young when you see a paper you wrote in 1984. Questions? Yes. Please state your name and institution for the people outside.
Thanks for the really nice talk. I had a question. We have many systematics that only affect the signal. Okay. We have many systematics that only affect the signals. How are they treated in NPLM?
So yeah, we don't, I mean, when you do anomaly detection, systematics affecting the signals do not exist because you don't have a signal hypothesis to start with.
So if it's like jet mass resolution, jet mass scale, things like that.
Those uncertainties will affect your reference model. So the way you know, or how good is your knowledge about your background distributions. But since you don't have any assumption in signal shape, you cannot really encode any uncertainty in that. And yeah, and it's really not in the formulation. Yeah.
Thanks.
Other questions? We have 10 minutes. Go ahead, Jesse. Oh, someone in the back.
Thanks, Guy. Can you do the slide on the sparse Gaussian kernels? And I think I want to understand kind of two aspects of this. So one is just understanding, interpretability. In this particular case, you're designing a method where the learned values of mu and sigma have some meaning to it. And so the first part of the question is saying, can you just describe the difference between using that type of functional form versus just saying, let me look at places where my F function is large? Like, why is it superior to be thinking about learned values of mu and sigma for thinking about that problem? And then the second question is maybe a more technical one, is that there's also the question of dynamics about whether you can actually learn this. And if I have like some narrow Gaussian bump someplace that needs to, as you said, kind of competition is trying to go in different places, it's like, it can be hard to gradient descent find your way to move that bump around. So in terms of like just the dynamics of that particular functional form, how easy is it for us to learn that structure and get reasonable values of mu and sigma?
Yeah, so in this model in particular, the sigma, so the width of the Gaussian is fixed. So it's like in the previous cases shown in the previous slide here. I start with a specific choice with the idea that I could make multiple tests after. But and the reason why I'm doing this is really about making the training stable. I can comment about it later, but it is that you define a family of functionals where sigma is fixed. So that's not trainable. What you train for is the location of the kernels and the amplitude of it. And yeah, the way you can enforce exploration of the phase space by letting this kernel learn their optimal position comes really from the choice of the loss function. The loss function sort of defines essentially the landscape you need to go over. And if you use as a loss function, you could think of a binary cross-transform. I'm using the normal Pearson loss. That essentially naturally creates a sort of some forces that are repulsive or attracting, and these are forces that are, let's say, caused by each data point. So the whole dynamic depends on the specific data set. And the overdensities are essentially attracting basins for kernels with the positive coefficients. Underdensity are attracting basins for kernels with negative coefficients. And these kind of forces sort of make the the kernels move around and adjust themselves in the landscape. So that's the way it works. It's actually hard I mean, it's like the training needs some regularizations, and I've been doing some experiments with different choices of the model that I haven't showed here because they're still really ongoing. But you can make these organizations of kernels even more clever. But yeah, I cannot really give you any result concrete yet on that. About the interpretability, you're right. I mean, one in principle could also think of having a model that doesn't require locality somehow, doesn't require a kernel to be placed in a specific location where the anomalous area is, and you still will be able to maybe extract some meaningful knowledge about it. The idea of sparsity in this case is that if you can make or get the same kind of scores that you will get with a very complex model with something smaller, you really can look at the analytic form of these models and try to use these analytic forms to maybe think of interpretability or thinking of an analytic model for talking to theorists and say, okay, this is the functional form that is describing the shape of the anomalies over there. And while if I was thinking of doing this, for instance, with 1,000 kernels rather than 10, I would have to combine many different, let's say, components in my function, and that would be, at some point, will become untreatable. Or if you think of neural networks where it's not really clear which parameters affect what in terms of like final output of the score, then like using this information to kind of say something about the shape or the impact of specific input features into the score becomes harder. So I think it's just making it more open for people to understand what's going on. That's the idea, or the way I will define interpretability at this point. And the other point about interpretability that I will make here, and the sort of relates with the idea of sparsity, is that this is really keeping the model small, means also compressing the information, or really trying to understand, distilling what are the relevant features for each data set that you want to capture. So it's a way to also think of summarizing information and really require the model to choose what is really relevant.
Thanks.
Meanwhile, I thought of something and there's no, oh, yes, there is. Go ahead.
Thanks for the nice talk, Gaia. I hope this is a reasonable question. We mentioned already in talks on the first day about AXLITTLE, which is an anomaly detection in the level 1 trigger system in CMS. And we talk about using anomaly detection in the trigger systems because it's a nice way to maybe scout for unusual data, and it serves as a hotline, and we can further do analysis on those data, or maybe develop dedicated triggers. So that's one use case. And so there we're applying a threshold on the score, if you like, and then looking at the data that pass that threshold. In the case of, say, level 1 scouting at CMS, which is something we're looking at. So on the slide 22 that you just showed, for example, I mean, you show a histogram with some hundreds on 22, sorry. So it was involving, say, model selection. But my question is general. I mean, here you've got a histogram with some hundreds of events in, for example. I mean, what challenges do you think you might face for anomaly detection on a statistical basis if we have like 1 billion events in that histogram? Because in one Lumi section at the LHC, which is 23 seconds, with a system at level 1 scouting, we have 1 billion entries or more.
Yeah, that's a good point. It was one of the things I was going to comment about, but I kind of cut because of lack of time. So I'm happy that you asked this question, which is like, yeah, one of the challenges about like trying to reduce assumptions in the experimental pipeline, like trying to go triggerless, for instance, that what you mentioned right now is that we will have way larger data sets, and we already have large data sets, and going even larger or acquiring all this huge amount of data will become challenging. And like one thing I think we should start thinking about is how can we make this kind of tools being usable in a quasi-online or in a quasi-online way. So somehow thinking of performing analysis almost online, such that we can kind of look at some data while we have them and then throw them away and save more data because we just cannot store everything. And yeah, so one thing I was like I've been thinking about, and I show here in the slide, is how to perform this classifier to sample test in batches, or splitting the data and parallelizing this training, such that without essentially losing sensitivity by splitting or by reducing the luminosity of the single sample. And there are ways, for instance, we could think of doing this and aggregating such that the sensitivity is completely restored, like if you were looking at the full set of data points at once. The other thing that maybe your question was about is, let's say, distortions in the data distributions that become very relevant because of the high statistics of the data of the data set itself. So if you have some let's say mismodeling that is due to some experiment, some systematic answer, or some miscalibration of your detector, and those become essentially relevant. How do you make sure that you don't capture those as anomalies and you are able to recognize them as uncertainties, or like within the uncertainties range? That's something that I think, because we are seeing this challenge for the first time now by, for instance, talking about CMS, by looking at untriggered data sets and these large statistics, is something that we really need to think about. But I think, as always, that we will, I mean, we've said this already, we'll never have a perfect model of our data under normal distribution, under normal conditions, or this null hypothesis. We always have some biases coming up, and eventually when you increase the statistics, you will start seeing mismodeling of our physical models of blood. And the solution eventually is understanding how to add to this model the right statistical uncertainties, such that this kind of distortion can be mitigated, or are recognized and controlled. I think that's the way we should go.
Okay, thank you again.
Thinks. Okay.
This one was pretty good, so you don't have to come close or anything. Just speak.
But I have to stand still.
Well, if you really want to walk a lot, we can also give you.
Yeah, exactly.
Oops.
I have to stand on this side to
Okay.
introduce you. That's right. Okay, I'm pleased to introduce our next speaker, Thea Aristad from ETH Zurich, right? Detecting new physics as data anomalies at the LIC, transitioning from toy data sets to millions of protons, collisions, billions actually.
Billions.
Trillions.
Yeah. In this case, millions.
Oh, great.
All right, thanks a lot for the introduction. So with this talk, I want to follow up a bit on the two previous talks where you've seen that anomaly detection is slowly turning into something we're trying to use a lot in our field, and a kind of case study from what we went through from the R&D studies we did on toy data sets to actually applying it to PP collision data. So if you look at Inspire HEP for papers on anomaly detection in our most common physics categories, you can see that there's been a lot of papers published on the topics, especially in the past couple of years. So 2023 was 40 papers, this year 16 papers. But when you look at how many of these methods have actually been applied in big experiments like ATLAS and CMS, it's way less. So for instance, for ATLAS, there's been 5 papers on anomaly detection for searches, and in CMS, 11. So that means that there's this sort of gap between R&D studies on anomaly detection and actually using them to analyze collider data. So a couple of years ago, a group of us at CERN decided to go together to take a bunch of these different types of methods with very different properties and actually take them from concept all the way through to an actual physics result. And what we started with looking at was kind of the lowest hanging fruits. So once you're in a big general purpose collider like CMS and ATLAS, the very first search you do once you have new data is a search for a heavy particle decaying into 2 jets. So here you can see the search we did with the 7 TeV, center of mass energy, 8 TeV, and 13 TeV. I'll talk more about what this search actually is afterwards. What you can also see here, you can see the total amount of data that we actually collected each of these years. These are published very early when we just have a small fraction of the data set available. That's because these searches are very easy to do, and you can probe a vast amount of new physics signatures in this final state. However, we haven't yet looked for all types of new physics particles in these final states. There's a lot of phase space left uncovered. For instance, if you look at very small couplings or decreasing energy, there are very many potential corners where new physics signatures can hide. So here you can see an example of what type of collision events that we're looking at in CMS. So here you have a potential new heavy particle decaying into 2 jets back to back. And this particle we assume have some mass mx decaying into 2 jets with some other mass or quarks. So this is what it looks like. This is a specific event display from October 2017, where the total invariant mass of these 2 jets is 8 TeV. So it's a very, very high mass event. And each of these 2 jets have the same mass of roughly 1.8 TeV. So here we're maybe thinking, this is maybe some heavy particle A that decays to a particle B and C. And these are in this case the same, both with masses of 1.8 TeV. Now, the ones who pay attention and look at this slide are like, okay, but wait a minute, this is not a dijet event. There are clearly 4 jets in this event display. That's because we're using something called Y jets that we call jets. But you could also say, hey, this is actually 2 small jets here that are very close together and 2 small jets here that are also very close together. So maybe this is a heavy particle decaying into 4 quarks or something like that. And then you say, why don't CMS and ATLAS search for that instead? This is obviously something decaying to 4 quarks instead, or to 2 fat jets with 2 small jets inside. Well, this we have actually also done. So here we have clearly said, okay, I'm no longer interested in a heavy particle decaying into 2 quarks, 2 jets. Maybe each of these jets have 2 small jets inside. And then we make specific selections to enhance our data in jets of this specific type. And these are also searches that we've done at CMS and in ATLAS. So we haven't found any new signal of a heavy particle decaying into 2 jets, but that doesn't mean it doesn't exist. Because for instance, when we look for those jets with 2 small jets inside, we think it's maybe a W boson or a Higgs boson or a C boson. We assume it has a mass inside this window. But you can also say, hey, maybe this jet has a mass outside of this window up here or down here. Also, we looked for things with 2 small jets inside, but maybe there are new particles with 4 small jets inside, or 5, or 6, or 7, or 8, who knows? And we should kind of look for all of these things. So what we wanted to do was design a very generic approach where you say, okay, my standard model background looks like this. It is a bunch of quarks that shower into jets, and they look like this. And I want to be able to discriminate this from jets with all sorts of particles and quarks inside, subjets inside. So what we want to look for is some heavy particle that decays into some other heavy particles or light particles, and we don't know what they are. So we have no clue what the signal is. We've just some vague assumption that it's heavy particle decaying into jets. So when we do these sort of exclusion curves, when we say, okay, this is the mass of a potential particle and this is the probability of producing it, we start kind of excluding these particles. We say, okay, everything above here can't exist. It can only live down here. And the name of the game that we try to do is we have a huge standard model background in these searches that we need to get rid of. So here you can see the standard model background in a variable of interest. So we want to reduce that as much as possible. And we want to be able to enhance some potential signal in the data as much as possible without knowing what that signal actually is. And if we don't do that, this background is too overwhelming to find the signal. You saw the plot from Gaia. It was a smoothly falling leveled exponential with a little bump on top. That little bump you can't see in this. So you want to get rid of this so that little bump becomes bigger. And we want to probe hundreds of signal hypotheses all at once because we don't know what signal we are looking for. And maybe even we can probe some signal that we haven't even thought of yet. So anomaly detection in analysis looks the following way. We look in some variable of interest. In this case, is this invariant mass of those jets. We saw before it was 8 TeV. If you don't put any anomaly detection threshold or anomaly score to suppress the background, you don't see this bump at all. If you can derive a clever anomaly detection algorithm that can tell apart a standard model jet from a new type of jet from a new type of particle, you can suppress this background significantly so that this bump is enhanced and you can actually get it out of your data. So that's what we want to do, suppress the background so we can see this bump. So if we want to identify these anomalous dijet events, there are different ways of doing that. And we looked at 5 different types of methods you can use, 5 different techniques. One is a self-supervised approach that we've heard about already, a variational autoencoder, trained self-supervised. And this we trained to compress and then decompress a jet, basically represented by a list of its constituents, in this kind of bottleneck lower dimensional embedded space. And when a new jet comes in that's not in the bulk of the training set, this compress and decompress sequence would fail. And you can basically use difference between output and input as an anomaly threshold, as we saw in the previous talk. Then we also looked at some weakly supervised methods. So what are weakly supervised methods? Weakly supervised methods is if you have mixed labels. Let's say you can't clearly label your data set, they're kind of dirty. So in this case, we say, okay, let's say we're looking in this dijet invariant mass. If I'm looking for a particle with a mass of 2 TeV, it's located here, not here, and not here. That means here you have a mixture of labels, the red and the green. This is signal, this is background. And this mixture is higher than the mixture of signal and background here. Then what you can do is train a classifier to discriminate between jets from these sidebands and jets from the signal region. And you can apply that classifier to enhance the amount of signal in your data set. And we're using 3 different types of approaches, koala, TNT, and cathode. I'll talk a little bit more about how they work afterwards. But this is the main principle. It's a simple MLP classifier trained on dirty labels that are both signal and background. Okay, then we used a hybrid approach that's called Quark. Quark is a dense, it trains 7 different density estimators using weak priors of the signal. So we train 1 density estimator for background jets, so QCD jets. Then we train 5 or 6 density estimators of representative signal jets. We choose some randomly, and then we combine them using an L5 norm. So we have 2 axes, and we take the jets that are the least background-like and the most signal-like, and we use those for analysis. So that's a hybrid approach. And in kind of the formalism we talked about before, this is a log likelihood-based approach, and these are likelihood ratio-based. So why are we using so many different methods? So we saw before they're kind of based on different principles. Also, some operate on the single jet level. So look for really weird jets. For the variational autoencoder uses each of these constituents inside the jet. These koala TNT uses high level features. So we've created clever observables. Or they work on the dijet system itself, which is the case for cathode and for Quark. The reason we're using all of these methods is that we don't know what we're looking for. So if we look at, for instance, 2 different types of new heavy particles, like here you have this W prime decaying to a final state with a lot of quarks, 6 quarks, here an X with 4 quark final states. If we looked at the Pearson correlation between all of these different methods, they're very uncorrelated. So most likely they have sensitivity to very different regions of phase space and very different types of heavy particles. And if we really want to maximize sensitivity to hundreds of new physics signatures, we want to use all of the methods we can think about. Okay, now, a lot of papers on using autoencoders for anomaly detection for high energy physics. How do we get it to work in praxis? So we can do this game of compress and decompress. And then we can use output minus input, reconstruction error, in this case just MSE, but it can be MSE plus KL, whatever you want. And we say the reconstruction error, if the reconstruction error is high, it's an anomalous event because I couldn't reconstruct the input well enough. It wasn't in the bulk of my training set, so it's a data outlier. Great, you select events based on that. You put that threshold on both of your jets and you say, this is my anomalous digit system. But where do you train this thing? Do you train it in simulation? Do you train it in data? If you train it on data, where do you do your analysis? So in this case, what we actually have to do is we have to say, okay, this is our data set. We have to be able to define a control region where we can train our data in, where we can train our algorithm in, which is not the signal region, because that's the region we actually want to test the data. So we put a cut on a variable that's loosely kind of signal dependent already. So we're already saying, okay, we're looking for a little bit of a specific final state so that I can train an anomaly detection algorithm in a sideband and apply it in a signal region. So I have two orthogonal data sets. The problem is that once I then train the algorithm there, I apply it and then look at the digit invariant mass, you have what's called an AI bias, basically. So before you put the anomaly threshold, you had something that was smoothly falling. After you apply a cut on that anomaly detection score, you're strongly biasing your selection. So this is kind of fairness in HEP. So here you have this strongly sculpted distributions. So what we have to do instead is decorrelate that cut on the score from the variable of interest. And for that, we use something called quantile regression. So what we do is that we train a quantile regression to find a cut as a function of the variable of interest that corresponds to a fixed percent of the mistagging rate. So we want a 1% mistagging rate, then we train a quantile regression to find the best cut, basically, so that it retains its smoothly falling shape. We have to do that in the signal region. And in order to smooth it out, we basically do it 3 times, then apply it to the 5th, 3 times apply to the 5th, and we rotate through the data that way. And then we get smoothly falling digit distributions that we can search for a bump on top of. So here you can see kind of what that looks like. We have a smoothly falling distribution that we can easily fit with a smoothly falling exponential and extract a bump on top of that. Getting weak supervision to work in practice is also not so easy. So here we train a classifier to discriminate between this region and this region here. We can do that in 3 different ways in our case. One is using what's called koala, where we say, okay, data here we label signal, data here we label background, and we train a classifier to discriminate between the two. Tag and train uses an autoencoder to further enhance the signal fraction in this region. And cathode actually learns a conditional density from the sidebands, interpolates it into a signal region, and then trains a classifier sampling from the density function versus the data itself. And then you have your classifier that you then apply to data. How much time do I have left? I think it should be 10. Is it not 20 minutes? Oh, okay. 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 And so here, since we have these sideband definitions, we look for a bump in this region, and we use these regions as sideband regions. But of course, you can also assume that the signal is between these regions. So we always have to have regions in between to ensure we catch the full signal. And here you can see an example of what that looks like. So for every single of these bins, we do a search. These are our sidebands. We train a classifier to distinguish this region from this region, and then we apply it to the data. So what's really cool about these methods
is a very confusing plot, but I'll try to summarize it. So as a function of the amount of signal you inject, if you look at the p-value you extract, this is what you get if you use the vanilla approach of not applying any anomaly score at all. If you apply a traditional method of substructure selections, you can improve that down to something around here. Then using these anomaly scores instead on top of your original selection, you can really push the p-value down here, which can take you from an observation to a discovery, basically. So this is very, very powerful. I'll skip this. It's interest of time. So the main point here is that there are some quirks when you want to set limits, which is that the signal efficiency depends on the amount of signal you have in your data, which means you have to estimate upper limits in a very different way than in the classical search. You want to talk about this? Yeah, no. Okay. So what's really cool here is in this search here, you can see the upper limit on a bunch of different types of signatures where you have different types of prongs in the final stage. You have a jet with 2 small jets inside, 3 small jets inside, 2 + 4, 6 + 6. And we can set limits on more than 50 different new physics hypotheses, all in one go. And a lot of these cases, it's signals that has never even been searched before in any analysis. So, okay, you maybe can't detect things you never thought about, but you can be really efficient looking for basically everything all at once with one tool. So finally, in this plot, we saw there's also some particles that have not been analyzed. So what does that mean? That means that the QCD cross-section, the probability of producing events we're not really so interested in, is so high that most of our data is only junk. So we have to put trigger thresholds on the data we select, which means that there are regions of the data that are not even accessible to us in analysis. So in the CMS detector, where we collide particles every 25 nanoseconds, we cannot keep every single collision. So what we do is that we look at the data ultra fast within 4 microseconds, and we reject 99% of the events instantly. And the way we reject those events is by cuts on, say, mu1 energy or jet energy or E gamma energy. But you can, of course, imagine that new physics falls below this threshold. So what we've been doing in CMS is rather select events based on their degree of abnormality. So use an anomaly detection algorithm, only select abnormal events. And this is currently running inside CMS, taking 300 anomalous events per second, and it's what we call axolitl. Axolitl is an event level anomaly detection algorithm. It looks like missing energy, electrons, muons, jets. Does this vanilla variational autoencoder procedure of decreasing the dimensionality to a lower dimensional embedded space, sample from the Gaussian distribution, and reconstruct the event again. The problem for us is that this whole algorithm took 125 nanoseconds, so we couldn't put it inside the trigger. Our constraint was having inference done within 50 nanoseconds, so this wouldn't work for us. So what we do instead is that we say, hey, let's only use the KL part of the loss. We use only the latent space, only the mu's and the sigmas from this latent space, and use that to select events instead, which means you've chopped your network in half, you don't have to keep the input around, and you use the embedded space itself to select events. And then we keep all of the events that are above that threshold. So the challenges here has been, when do you train? Because we know that conditions in our detector changes all of the time. So maybe you sometimes have a little piece of ecal that switches off, or we have new jet calibrations, etc. And so this has also been really, really tricky in practice. So what you can imagine is that you first train the algorithm, then you deploy it and take data with it, and then suddenly someone derives new calibrations, you have to retrain and deploy again, and so on. We can't use things like continual learning, for instance, because our firmware is updated in regular steps, and you have to be part of that firmware release, basically. What we can achieve with such an algorithm is if we add 1,000 events on top of the normal rate with axolitl, this is, for instance, for a Higgs decaying to 2 scalars decaying to 2 power b's, you can get roughly 50% increase in your signal efficiency. And we see this is generic for a lot of different signal hypotheses. You can really increase your sensitivity to a vast amount of new physical signatures. So we can do both of these, model agnostic and data driven, and exceptionally fast. So I wanted to end with this. These are two event displays of the two most anomalous jets for the offline search, where you have an invariant mass of 3.5 TeV, two anomalous jets here, and the most anomalous event that we triggered with AXO Little this year since start of data taking in 2024. And if you don't believe anomaly detection to search model agnostically, you can believe it for catching a lot of new hit physics signatures at once. Thanks a lot.
Questions for Thea? Olaf.
Yeah, very nice talk. I have actually a question to you and to Gregor. Gregor, you presented 2 years ago some summary of the LHC Olympics. And I remember overall the outcome was that is quite challenging, and there was like a signal injected DB, some with 2 and 3 jets, and was not found. So my simple question is, would you do better now?
What do you do with what?
What we do better now? Do we have improved the methods that we would do better now?
What we improved since the...
I think the answer is yes. So if you're asking, essentially the LHC Olympics was a competition to test anomaly detection techniques. And since it came out, I think both Thea and Gaia highlighted many of the new papers on anomaly detection, and people are keeping on pushing the benchmark score on these data sets and extending it to new regions. I think the best number right now, we need to talk to Vinicius, who improved like the best score on the LHC Olympics by a factor of 4 compared to what was the best 2 years ago.
Okay, thank you.
In the back. Oh, sorry. Sorry, you're next. Too late.
Hi, great talk. For autoencoders, or I guess the general setup for that we have in the particle physics framework is overdensities. Is there not a worry with autoencoders that in the input space as well, that these things don't appear as outliers or out of distribution in this input space, but also as overdensities, and then would kind of invalidate using autoencoders?
It is also a little bit why we're using very different methods, some really targeting overdensity, some targeting out of distribution points. But what we also see is that in this 57-dimensional space, or in this case, 100 by 300, huge dimensional space, data outliers in that space maybe are overdensities in the 1D plot, basically. But it is one of the reasons why we're using all of these different methods, because we really just, we don't know.
Thanks.
And there will be a follow-up paper to this physics paper with really the methods, a detailed study on narrow versus broad resonances, etc.
Yeah, thanks for the talk. I was curious, so maybe I didn't catch it. So there are multiple methods, right? And as you said, they're all sensitive to basically a different set of alternatives, probably. And so I was just curious, in terms of like the online selection, like how do you kind of prioritize one method over the other? Like, do you take like a bunch of bandwidth and you put, you know, some hertz on this method, some hertz on that method, or?
Selections, you have 50 nanoseconds and very little bandwidth because you're competing with basically the whole experiment. For the online selection, we have one global event selection algorithm.
That is like a big OR between all the...
It's an OR, it's one for us in OR with, what is it, 124 of the other mu1 PT over this and that.
Okay,
And then there's a dedicated stream of level 1 anomaly data.
Okay, and so that one OR, how did you decide? I mean, because you have like all of these things, so is it like some kind of average of all of these decisions, or?
For the online algorithm, there's just one algorithm. For the offline, there's the 5. For the online, it's just one autoencoder that takes all of the objects, the high-level objects.
Okay, okay. Right.
And should hopefully feed to, if you're doing dielectron, dimuon, 8 soft jets, everyone.
Do you know what the interaction is? So does that one algorithm kind of favor one of the cathode or TNT or koala?
We haven't touched them together yet. So there's been no search on top of AXO yet. We've only taken data since April.
Okay.
And there, obviously, the things we talked about, like sculpting and the variable of interest, will probably be a huge thing because we're taking event level information. So if you're looking at dimuon invariant mass, there's no guarantee that's not going to be just a bump on a bump you're looking for. So.
Right. Thanks.
We'll wrap it up. In that case, thank you again.
Can I use the mouse to? Yeah, that was the way forward on the participants. And is it just click to go forward or space? Yeah. Both work.
And this microphone should be fine.
You don't have to talk, especially now that it's pretty good in catching.
Easy. How many minutes did we tell you?
I think it's 20.
20 out of 25. We'll change the ratio.
Let's see.
We'll go with 20. That's what we'll do. Okay, so now next up, we're pleased to have Andre Scafidi, anomaly aware machine learning for dark matter detection at Darwin.
Thank you very much. Thank you, and thanks again for having me. So we've heard a plethora of ML applications in LHC physics throughout the day. And that's been wonderful, but believe it or not, LHC isn't the only domain of particle physics. Unfortunately, the rest, well, in this particular case, things haven't been especially explored recently. And so here I'm going to present some recent efforts. But first, I don't think it was really necessarily gone over today, but I'll just brief introduction on dark matter as a concept. So I think a good fraction of the people in this room would know that most of the universe isn't actually comprised of stuff we see or can touch. Most of it is dark. And so we're going to be focusing on what, this constituent 26% odd that we potentially could discover, we'll see in a terrestrial manner. The search for dark matter has been extensive over the past 100 years or so, and the abundance of it, the abundance of evidence for it has just grown extensively. Gravitationally, dark matter makes itself known through a variety of channels, mostly astrophysical and cosmological, through the CMB, galaxy clusters smashing into each other and not behaving as they should, and stars orbiting galaxies faster than they should. And so, the idea is, if the dark matter is something that can at least interact weakly with baryonic matter, then perhaps there is a terrestrial avenue for detection. And so the idea is that, our sun is cascading through our galaxy and should be incident upon the sort of wind of dark matter kind of buffeting our solar system. Earth goes around the sun, and so why not try and detect it on Earth? And so hence here is the plug. So the XLZD consortium is a recent development. It's a consortium of 3 collaborations, 2 of which already have detectors operating, namely the Xenon and Lux-Zeppelin collaborations. Darwin has been responsible for a lot of the R&D for future upgrades for multi-ton Xenon-based experiments. The science reach for XLZD will be quite large, ranging from, of course, canonical dark matter models, extended dark matter models, axion-like particles, but also a range of astrophysical objects as well, cosmic rays, neutrinos, etc. Darwin specifically, so again, leading the R&D for these 40+ ton types of detectors for quite some time, but today I'll be focusing, of course, as is the theme, on the sort of preliminary ML and deep learning based tools that we've kind of been looking at to try and enhance the standard analysis pipeline in these sorts of detectors, with the collaboration paper coming out soon. So the current / future ML scope is quite broad. We saw some plots like this for Atlas earlier today. But today I'll be focusing on a sort of maybe a bit too grandiose, but sort of
wide, an end-to-end approach to the analysis pipeline that currently stands. And so first, it's probably important to understand how these sorts of detectors work. So XLZD will be a type of time projection chamber. The main idea is that you fill these things with dual phase liquid and gaseous xenon. You have two photomultiplier tube arrays on the top and the bottom. And the idea is that, you know, a particle will stream in, it will interact with a xenon atom in the detector. The primary scintillation, so photons will shoot off and deposit some energy in the photomultiplier tube arrays. This is what we associate with something called S1, a signal that we define at some initial time 0. Later on, any ionized electrons that were sort of liberated in the interaction will then drift up in an induced electric field, depositing energy into the PMT arrays in a much more enhanced way. And this is what we call S2. And there is some time difference between them. And this is all that we effectively get. Now, in the standard approach, all of this information that you effectively see depicted on screen here are represented with two numbers, namely CS1, CS2, standing for corrected S1, corrected S2. These are effectively high-level summary statistics that basically, give or take, parameterize an entire event within the TPC chamber. And these observables, these CS1, CS2s, these are basically a proxy for the recoil energy. So the energy of the event that was deposited in the detector, the energy being of prime phenomenological importance in any sort of physics you want to do. And so what is usually done is you write down, you know, if you want to do any sort of limit setting or sensitivity forecasting, you write down a likelihood function. And that is usually quite complicated, and which I've just sort of, for brevity, written down here as a science and an ancillary term. But basically, at the end of the day, it's in these, it's just a function in these parameters CS1, CS2, parametrically model dependent, and is effectively derived from extensive simulation and 2D templates that we extract for the various background components and signal, and we do the usual thing with this object. It is quite costly to do any sort of analysis because, you know, as one sees very quickly, these objects become, especially if you're doing frequentist analyses, profiling, etc., gets quite difficult with all the nuisance parameters involved. And so the question we want to ask is, well, okay, fine, this is all well and good, but is it optimal as a test statistic? Perhaps, perhaps not. Maybe we'll see at the end of the day that it's not necessarily. So I'm not going to go into too much detail about simulation-based inference. We've heard a bunch about it today in many of the talks, and there are some dedicated talks later in the conference by Will and some posters by Giovanni and Kai. But effectively, you know, the idea is, as I think Will basically knows, you know, if we can simulate a bunch of data conditioned on some parameters, we can train some model to extract an object. That object can be, you know, a likelihood ratio or just directly a posterior, from which we do inference. Now, here we're going to be doing something slightly different. We're going to formally follow the same process, except now the object that we're going to extract is not necessarily some sort of posterior conditioned on model parameters. We're not necessarily interested in that for this task, but rather, for lack of a better term, an anomaly score. And the aim of the game here is that we're going to sort of define, you know, an anomalous signal, let's say, as after data taking the observation of a significantly discrepant distribution of this anomaly score. So before we discuss how that works, we're going to briefly describe the actual data that we train on. So in a TPC experiment, there are two fundamental event topologies. These occur via two different scenarios. The first is the so-called nuclear recoil, which happens when a particle interacts with the nucleus of the xenon atoms in the detector volume. These are usually associated with WIMPs or the canonical dark matter candidates, usually. The second are these so-called electron recoils, which, as you could probably guess, is when a particle scatters off one of the electrons in the xenon atom cloud. These are the dominant background in these types of detectors. And lastly here, this is not usually necessary, but it is, usually desired to discriminate between these two in some sort of classification manner. And this is usually done by looking at the ratio of the peaks of the S1 and S2 signal and the time delay between them. But we're not going to have to worry about this. We're going to have something learners to do this for us. Okay, so the overview of the pipeline that we've got is very, very, very simple. Very, very simple architectures with very, very intentional jobs. So we basically have a variational autoencoder and just a classifier doing very specific things. The role of the autoencoder is to specifically learn the spectral information of the events. The classifier's job is to simply classify electron recoil, nuclear recoil, and we'll see why that's important later. We're just going to extract the elbow and the binary cross entropy from these models and just sum them with some scale parameter R, which scales the contribution of the binary cross entropy. You can ask me about that later. And we're going to construct some function or score, let's call it TS, that will serve in our analysis later. So the classifier here, just to note, because this happened recently, some recent literature showed that doesn't really matter what you use for this. BDTs work just as well as MLPs and transformers for this exact task, which I think is pretty funny. So all that matters is, as we'll see later, what actually happens when you do the classification is important for the phenomenology. So at the end of the day, what we effectively want to do here, as I'm sure we all see where this is going, is you want to derive some PDF F0, which is effectively the distribution of this, this function TS under the background only hypothesis. So what we do is we simulate sort of pseudo exposures, right? So we generate batched test ensembles. We weight them to their expected spectral abundance according to their associated backgrounds, which are known. And then we run them through the pipeline and we extract this, this function F0 here. So, of course, if I was to throw any pseudo data set that had some injection of new physics in it by design, this is going to manifest in the tails of this distribution, and we can reject the sort of null hypothesis via two-sample test or anything that you like. So I mentioned that this that the elbow from the VAE encodes the spectral information, as we'll see on the next slide. So the underlying energy of the events. The classifier here is constructed in a way that any of these electron recoils will be thrown to the left of this distribution, and any of these signal-like or any these signal-like nuclear recoils, which are the events we sort of really care about, are dragged to the right. And so this will kind of give an overabundance of those events if there are any dark matter particles present in the data set. They should manifest more if we throw them out to the right a little bit more here with this classifier. Okay, so the spectral encoding is pretty interesting to look at here. So on the right here, we have a two-dimensional TSNE of the 128-dimensional latent space of the autoencoder. We can see some non-trivial clustering of the recoil energy here, just from simulation. We know the labels. All the low energy events are clustered toward the middle here, high energy events on the outside. This is sort of what Jesse was referring to before as the low rank structure sort of deal going on here. On the left here, we can explicitly plot the elbow as a function of the recoil energy. We have these 1D marginals on the axes here. This is neat to show that in a completely unsupervised fashion, we can sort of not discriminate explicitly yet, but see a difference manifesting between what we would expect from background and WIMP distributions. These are unnormalized. These are not normalized distributions here. So, but regardless, it's nice to see that there's some non-trivial information being propagated here through the VAE. And so, I'm sure we all saw where this was going. In order to sort of reject the background only hypothesis here, This is an example of a pseudo data set with the benchmarks shown here. We now just construct a one-dimensional likelihood function here with the addition, now that we have counting statistics. This is a effectively a particle physics experiment. Things are going to be Poissonian. So we have some expected background number of events for a given exposure that we would expect to see. And so we can construct this unbinned likelihood function here. In terms of the PDF F0, and as you can see here, after I've injected a couple of pseudo data sets with some injected WIMP signal, the tails of this distribution here somewhat discrepant, and we can calculate a median sensitivity to reject the background only interpretation as a function of exposure. So the pros of this, okay, it's unbinned, again, parametrically independent on the WIMP model or the dark matter model, which is not usually the case when discovery sensitivities are usually calculated for direct detection analyses. If assuming the simulator has suitably descriptive coverage, we won't need any sort of nuisance parameters or auxiliary terms. And more importantly, this can be augmented later with more fundamental data representations or calibration, which is currently what we're working on, by fine-tuning the model to more realistically understand how a real event would look, because the calibration efforts at XLZD are quite extensive, and we want to make maximal use of that. And of course, end-to-end computational efficiency is also a plus. This analysis can really take on the order of seconds as opposed to sort of hours. So just some results. So we can basically plot the median sensitivity as a function of exposure. For this method here in blue versus the sort of baseline likelihood approach for the analogous background rejection test. And you can see it just far outperforms. Here, if we just pick an exposure and I just actually plot the toy experiments and the relative distributions here of this one-dimensional likelihood function that I showed earlier, you can see that for this deep learning-based method, we can see greater separation between the distributions from the cartoon I was showing earlier. Basically, this is the analog versus the exact analog for the current baseline approach. Okay, so summary. This is one of many things that we're kind of working on, but the XLZD ML program is making way. Here we focused on the sort of first run of a sort of novel end-to-end method for looking for anomalous physics in a given data taking. It looks like it works. It far outperforms the baseline likelihood approach for the analogous test with a drastic increase in computational efficiency. And it's going to serve as a sort of novel baseline for future modular additions. So whether that comes from calibration data and domain adaptation, explicit energy reconstruction using SBI, and time domain PMT readout handling, which is a significant challenge, but we're working on it. That's it. So thanks for listening.
Thank you for more than sticking to time. Questions, Rondre? Yes. Lydia.
Hi, thanks for this talk. Very interesting. I had a question relatively at the beginning. There's no slide numbers, but I think it was at around slide, I don't know, 13, 14 or something. Because yeah, no, that there. Yeah, here. So from here, you went on to the next slide where you've shown that you can go to this different space. And I was wondering what happens to your parameters theta in this case, because your R in principle is still dependent on this.
Yeah, so theta now just represent, so I mean, here it's sort of a cartoon, but here, I mean, we would explicitly simulate data for background. So theta would be theta naught.
Okay, so you would assume that you sort of perfectly understand all of your.
Oh yeah.
Okay.
Yep. This is what happens all the time, regardless of any analysis. there's always a degree of faith with respect to how well you understand backgrounds.
Okay, thank you.
Yes? You have a question? Yeah. For Andre? Louis has. a lot to ask questions.
I missed, what is it in the machine learning approach that's giving you this much better performance than in a standard approach?
So, yeah, so I think it's in the standard approach, right? So when you calculate these high level summaries, so when you calculate these CS1, CS2, there's a significant degree of information loss that's currently occurring. What we do when we use this approach in the sort of the simulation-based approach is we're effectively using the same simulations that basically fundamentally go into the construction of this CS1, CS2. And so all of that information is propagated with significantly less loss via attenuation in the neural network, as opposed to just calculating these two numbers. So in effect, we're doing the same thing with less reliance on analytical assumptions, of which there are a significant degree that go into calculating these high-level summaries. Yeah, among a multitude of other things, but it's basically this is what we associate the degree of increased performance.
I've never seen a likelihood ratio do so badly. I've always, if you're right, it's a theorem. If you write down the right likelihood ratio, you
well, that's the thing. Is it the right one? I mean,
clearly not. Yeah. So
yeah.
So I had a question. If there's a blip in between S1 and S2, again, the likelihood ratio, you didn't mention how it wouldn't reject that, but I guess this would reject it, right?
In principle, yes.
Yeah.
At the moment, we haven't really. So in a way, we're working with slightly tuned data in that this S1, S2 separation has been pre-filtered. We're working on a way to do that ourselves and integrate that into the entire pipeline. But in principle, yes, it should detect that too.
Okay, well, let's thank Andre again.
It's been like 20 or
Okay.
so.
Okay.
All right.
So we're happy to have Josh Villarreal from MIT, who's going to tell us how to speed up Feldman et al.
That's a tall ask, but so hi everybody. Yeah, I'm Josh. I'm a grad student at MIT. Not to jump on the LHC hate train, but I do neutrino physics, so I should preference that. And very excited to be here today to tell you about how we've been applying simulation-based inference into stereo neutrino global fits. It's a big part of our group at MIT. So I have the obligatory slide about neutrino oscillations. So in the standard model, neutrinos are neutral leptons that interact via the weak interaction. The flavor eigenstates, which are like electron-like, muon-like, and tau-like, denote how these neutrinos interact in a charge current interaction. Their mass eigenstates are how these neutrinos propagate through space and time. In 2015, the Nobel Prize was awarded for the experimental observation of neutrino oscillations, which means that your mass eigenstates and your flavor eigenstates are misaligned with one another. So if you produce a neutrino of one kind, of one flavor, as it propagates, it'll sort of spontaneously morph into another flavor. When you go through the math, the survival probability or the appearance probability can be parameterized by elements of something called the PMNS matrix and a mass splitting, which has to do with the mass differences between these different oscillations. And basically, when you plot a neutrino's survival probability is a function of length over energy. Baseline over energy is I'll sometimes refer to in this talk. You get something that looks like a sinusoidal curve. That's that. And then experimental observation of neutrino oscillations also has an important consequence, which is that neutrinos have mass. At least 2 of the neutrinos have mass. That's required for that like tower of states to kick off the oscillation phenomenon. Okay, so if you permit massive neutrinos into the standard model, you also kind of make yourself susceptible to the possibility that you have access to a right-handed chiral neutrino, which does not participate in the weak interaction, and this is called the sterile neutrino. Because these sterile neutrinos aren't accessible by the weak interaction, they're only accessible through oscillations. And so the way to do that is to add an extra row and column to your PM&S matrix. And now you can sort of fit a more complicated sinusoidal curve to your data. Neutrino physics is, under a lot of tension right now is the technical term for that. There are anomalies sort of with appearances and disappearance left and right. When you incorporate additional neutrinos into your physical model, you will have like a 3+N sterile neutrino hypothesis. 3+1 is the model that I'm going to talk about today. It doesn't solve the problem. If you pick a number between 1 and infinity, there's a theory out there with that many sterile neutrinos. And there are some computational barriers in place that make fitting these sorts of curves a little bit more difficult. Like I said, the simplest model which permits sterile neutrinos is 3+1. So that's what I'll talk about in this session, specifically as like a test bed for how to apply simulation-based inference to global fits. I'll talk about electron neutrino or electron antineutrino disappearance experiments. And so I have that oscillation probability up on the screen. The name of the game is to measure UE4, which is that corresponding element in the PM&S matrix extended for the sterile states, and the mass splitting. I'm also talking about light sterile neutrinos. So this is like a mass splitting kind of in the range of like an EV squared. At the top right of your screen, I've showed like the flavor content of each of these mass eigenstates. And then on the bottom right of the screen, a big complaint that I have is if you don't indicate what's excluded in the exclusion plots, I can never figure it out sometimes. So if you see something that looks like a vertical curve and then sort of cuts to the right on this plot of UE4 on the horizontal and delta M squared, that's an exclusion. So we're excluding everything to the right of that curve. If I show you a closed contour, that means what's inside the contour is allowed. Okay. So there are 2 classes of experiments that are important that I kind of give a brief overview to sort of, stage the arena, I guess. And these are the reactor experiments and the source experiments. So a reactor experiment kind of works by you have some nuclear reactor core at a research or a power reactor, which is constantly producing, neutron-rich nuclei through fission. These neutron-rich nuclei will beta decay and will produce a flux of electron antineutrinos, typically in the range of like a few eV. Sort of what you do is you then pair a detector, which can detect these electron antineutrinos by inverse beta decay, with your nuclear reactor at a combination at a baseline that sort of matches that L/E that I was talking about earlier. So these are like, I think, tens of meters away or so, to give you an idea. I know that in neutrino, there were some comments about this that, have like added more stake in the game. But historically, we've referred to the weirdness in the reactor experiments as the reactor antineutrino anomaly. This is because of a mismatch in flux that's measured in your scintillator detector and a flux predicted by, sort of like first principles calculations of how many neutrinos you expect to make in your nuclear reactor core. Obviously, nuclear reactor cores are extremely messy. This depends on like concentrations of uranium and plutonium that you're sort of burning. And so there's a big uncertainty on that normalization. And so in 3+1 fits, typically what we do to account for that is do something called a shape only fit. So rather than sort of measure this normalization mismatch and call it quits there, instead the strategy is to sort of like account for that mismatch in normalization and fit that sine squared curve directly. That'll impact the region of parameter space where you're sensitive. So these experiments have a lot to say for mass splittings that are like a little above or at 10 eV squared. And the stereo experiment, which runs I think at ILL, is shown below, but Prospect, Naos, and Dance are 3 other experiments that are included in this category. The second class of experiments that I'm going to talk about are source experiments. So the way that these work is you have a electron capture decaying isotope that you place in the center of a gallium detector. So something like argon-37 or chromium-51 will produce a well-understood flux, a very well-understood flux of electron neutrinos. And when these electron neutrinos find a gallium atom, every once in a while, it'll convert the gallium atom into a germanium-71. And then periodically, not on an event-by-event case like the reactor experiments, you can count the atoms of germanium-71, and this gives you some information about how many electron neutrinos you measured. Because of poor segmentation, these detectors don't have a fine enough binning and baseline, basically, to be able to like measure the shape of the sinusoidal curve directly. However, because the fluxes of these isotopes are generally pretty well understood, you can get a good normalization measurement. And this mismatch in normalization in this class of experiments is known as the gallium anomaly, if you've heard of that. The configuration for the best experiment is shown on the screen, but SAGE and GALAX are also included in this study. So the idea is that for 3+1 searches, the reactor experiments don't seem to have a real preference for one additional sterile neutrino. The gallium experiments do favor this because of this like normalization effect. And they also sort of explore different regions of parameter space for that reason. So these are sort of kind of ideal test bed for sort of resolving tensions in these kinds of fits. So the way that you would typically do this if you were in like a intro stats class is you would compute a likelihood all over your model parameter space. So in this case, UV4 and delta M squared. And then what would happen is you'd compute some sort of test statistic like a likelihood ratio against some null hypothesis, which in our case is just 3 standard model neutrinos, oscillations consistent with the standard model. You would then use Wilks' theorem to associate a probability density with that test statistic. And then from that, you could compute p-values and confidence regions and all of that good stuff. There are some well-known issues, though, with applying Wilks' theorem, especially when you fit neutrino oscillation experiments. Number one is that your null model sort of sits at the boundary of your explorable parameter space. And then the second one is that when you fit an oscillation frequency, you actually kind of screw up the degrees of freedom in the chi-squared for your log likelihood ratio, rather. So this is kind of because when you allow the frequency parameter to vary, it can kind of independently check many local minima in your model. And this can cause you to misrepresent confidences when you draw an exclusion curve or a signal region or something. So this is a well-known issue. And then at the bottom of the screen, I've shouted out my colleague John, who has been helping me with this, and he has a great pedagogical overview over sort of applying this in practice. So I recommend you check it out. So the answer to this is, as Bob Cousins generally introduced me, Feldman Cousins. You can't necessarily just like say that your likelihood ratio falls under some sort of well-defined statistics. Instead, you have to sort of measure that empirically. So the way that that would work is you would take a fine enough grid over your model parameter space, you compute something like a likelihood, and you compute something like a test statistic, and then you sort the values of your test statistic in order from most desirable to least desirable. And then you take your basket and then you add eggs being points in parameter space into your basket until your desired confidence region has been reached. And that can be computed from the likelihood function that you defined earlier. There's some problems with this. Likelihoods are hard to compute. Test statistics are hard to compute. You have to do this on a really fine grid in order to like draw contours effectively. And also the problem gets more complicated in the situation of global fits because now you're considering many experiments simultaneously, which could possibly have like correlative effects or that sort of thing. So in general, this is considered to be like kind of state of the art, but it takes a long time to run. And for that reason, it's not frequently applied to many experiment global fits. So quick one slide about simulation-based inference. I know you've heard a lot about it today, and it seems to be
you know, a great motif of this week. So the idea is that you can basically use some sort of machine learning model to learn a posterior distribution or a likelihood or something to help you draw credibility regions or confidence intervals or that sort of thing. Basically, as we get better at density estimation, we expect that these kinds of techniques will get better also. The first thing that we tried in like very early stages of this work is just to apply an old paper from 2015 that we thought was kind of interesting. So the idea is that Gal and Garamani basically showed that when you train a neural network, just a fully connected neural network with dropout left on at inference time, you are effectively training, like asymptotically, you're minimizing the same thing that you would minimize if you train like a deep Gaussian process or something by minimizing like a KL divergence. This is a cool paper, and basically the idea is that sort of intuitively, as you're making each training step in your model, you're sort of instructing like all of these kind of sub-networks on how to vote for your final outputs, and then you can fit something like a KDE to that, and you get some kind of posterior over your parameter space. When we give that a try, we see a structure like this. So what I'm showing here is the colors are the neural network's ability to reconstruct the oscillation parameters. White is good, blue is bad. And I show these for 3 cases. I show these for stereo only, I show this for best only, and then I show this for all experiments simultaneously. So you see when you're kind of inside the region of parameter space where your model is sensitive, these are kind of fitted from doing many sort of simulated exclusion curves. You see a region of parameter space where the neural network does a pretty good job at reconstructing the oscillation parameters. But then there's this like very clear circular contours in the middle of the plot, which sort of corresponds to like an R squared equals 0 guess. So what happens there is if you just fit like a horizontal line to any data or something, you're just going to guess the mean every time. That's sort of definition of R squared equals 0 if you were to run like a linear regression. And these neural networks are doing the same thing. They can't really infer what the true underlying oscillation parameters were. They just sort of make their best guess by averaging all of those points in parameter space. And that's why you see that structure in the residuals. Obligatory slide about normalizing flows. This is the picture that you pull. So basically, we can correct for this by learning how to transform that probability distribution out of the dropout network to a space over the true underlying oscillation parameters and kind of smooth out that that spot that you saw in the center of those 3 slides. So with that together, we can build a probability density, which in this case is a posterior, and then sort of build a 2D region of credibility from that. And we expect like sort of nominal correspondence with what you would see from like higher fidelity fitting frameworks. Okay, so these are preliminary. This is a prototypical kind of phase of this work. And there's a lot of model tuning that we need to do. But nominally, we're excited by what we see. On the 2 plots on the left for stereo only and best only, the dashed line again corresponds to a sensitivity that you would compute from higher fidelity sort of fitting frameworks. And we kind of see that in our posterior, we generally find that regions of the highest probability are to the left of those sort of exclusion curves or to the left of those sensitivities. With minimal increase in computational runtime, we can apply this for the full global fit to kind of get an idea of where in parameter space we're sensitive to. But for like a null-like example where none of these experiments even alone would be able to pick out what the best fit point is, we can sort of assign like a similar sort of contour. And then when we inject sort of signal Monte Carlo samples, we recover close contours when we would expect it. The structure of the best and the all experiment contours might not be super intuitive. So the way that it works is that best sees a normalization effect, like I mentioned. This is driven by the gallium experiments. When you are computing this normalization, basically the networks or the fitting framework has learned that it's probably a very, very high delta M squared relative to your parameter space that you're exploring that's generating that data. This is because when you average over a sine squared curve, you get like a half or something. I think that's right. And then you basically end up with like a reconstruction of that normalization mismatch. So that's why best and like the all experiments together sort of shoot up to the top there. They're like correctly fitting that it's like a higher value delta M squared that's sort of responsible for generating that signal. And then, this is fast. I think an important benchmark to compare this to when doing any kind of surrogate modeling is like how long the whole process took you together. So the data generation step for us, I think we ran on a grid of like 100 by 100 points in the parameter space. And we had 50 model realizations for each of these points. So generating that data, training neural networks, normalizing flows, and evaluation takes about 2,500 CPU hours compared to higher fidelity fits. This would take a few orders of magnitude longer in runtime. So that's pretty nice. And then also when you're going to do something like simulation-based inference for global fit, it doesn't really hurt you in the long run to incorporate more experiments into your fit. This is nice because also if you see like a weird kind of fit result in the end, a lot of times what you'd like to do is fit these experiments kind of individually with one another and sort of like identify what's driving that like sort of anomalous behavior. And so for something like this is a great application of SBI. Something that we're also interested in exploring, particularly with the issue of the normalization, the flux normalization and the reactor experiments. The uncertainty on that flux estimate isn't Gaussian. And so by sort of simulating this under non-Gaussian uncertainties, we have to make minimal changes to this kind of framework to test those kinds of hypotheses quickly. This takes some pretty careful tuning. I think that, like I said, Feldman-Cousins is kind of state of the art, but the fact that, bang for your buck, we can get pretty close is exciting. So yeah, hopefully I've convinced you that SBI is nice for global fitting, particularly nice in its application to oscillation experiments and global fits of stereo searches. We're excited about the direction that SBI is heading to augment or perhaps even one day replace higher fidelity fitting methods. So thank you very much.
Thank you, Josh. Questions for Josh? By the way, I was remiss in not checking outside. I don't even know how to check outside. So if people outside can just speak up, I guess. Questions in the room? Lucas again.
Yeah, thanks for the nice talk. So I was just curious in the SBI picture. So how do you, so I mean, Feldman-Cousins kind of in the most general way is just kind of like the profile likelihood ratio test statistic, right? So in the presence of Nugent's parameters. So I was just curious, like in your SBI setup, do you somehow handle Nugent's parameters, or is the neural network parameterized by all Nugent's parameters and then you profile later on?
So we don't profile, and this is just like a typical kind of posterior density estimation. So we don't profile over like a test statistic like Feldman-Cousins would. Like we're interested in exploring that kind of thing, so like approximating a likelihood and approximating a likelihood ratio and kind of seeing how that would go. Any sorts of like pulls and like subtleties relevant to any experiment come from the model we use to train these.
Right. Okay, so there's no, okay, so maybe it's a second order cousin once removed from Feldman-Cousins.
Yeah, cousin twice removed, yeah. Okay. Yeah, for an SBI thing, I had to go for points with the plant words, so that's what I could get.
Oh, so in fact, our paper did not have nuisance parameters. Many people may know, we found our paper in Kendall and Stewart, Gary did, and that has a profile to test statistic, which Kyle talked about years ago, Kyle Cranmer, maybe some others. But there was a separate recent conference on profiling versus marginalization, and there didn't seem to be a huge difference. And in fact, I was advocating more investigation of marginalization to compare to profiling. That'd be an interesting thing to do. Louis.
So, nice talk. At the bottom of your previous slide, you had a comment about the result is sensitive to the way you generate your Monte Carlo.
Yeah.
Can you expand on that?
So that's kind of like, so if you nominally, if you kind of like reweight where in parameter space you're sampling to generate the Monte Carlo data to train these models, we noticed that like the center of that spot would kind of move in space. And so we're kind of like hesitant also to the idea that if we do like a full 3+1 fit, we have to figure out how to correctly handle ways where like sine squared 2 theta EE, for example, would like overlap with itself, because that PM&S matrix element is allowed to like scan before 1 over the root 2 and like after 1 over the square root of 2. So that area of parameter space is double covered. So like I experimentally, like whether we sort of generated data in like log space or linear space kind of nominally kind of changed where we would end up drawing the contours consistently. And so that's something that we're going to continue playing with.
Can I ask Lou's question again, maybe just in a different language? So what I heard, it sounded like you're sensitive to the prior distribution over sampling in this space. Is that correct? When you say you're sensitive to Monte Carlo, that's equivalent to saying you're sensitive to prior over the choice of model parameters?
I'm not sure it's like sensitive in the sense that we can measure what the like prior was that was like underneath. I think the question is more like how you choose to sort of like one example that I can think of is that for those exclusion curves that I sort of showed, if you didn't allow UE4 to go low enough, the neural network that like sort of learns these embeddings in the first stage of this procedure would just pick an average inside like the signal region. And so in that sense, like how we sort of throw the Monte Carlo would kind of move around that like R²=0 center. Does that answer your question?
We can talk offline.
Okay.
Okay, let's thank all the speakers again, including. Do the organizers need to make any announcements before we? So we moved to posters, but it'll be hard to make announcements there, but is that the?
Okay, so we're going to move up to level 2 again. We'll have reception drinks, some nibbles, and then a poster section. To encourage you to engage with the posters and the speakers, we will have a voting system where you can vote for your favorite poster. There's 2 categories. One is particles related, the other is Astro Cosmo. You'll see scattered around A4 pieces of paper with QR codes and a link. We also posted the Maximus as well. So if you scan that QR code, then it's click to a Google form and you can vote there anonymously or anonymously. There we go. Please only vote once for the 2 categories.